How is better? It's loud. Yeah, it's the mic. Is it working?
Why don't you test your mic?
Okay. Yeah, good morning. It's
good
working.
Morning. Can you hear me? Is this mic working? Okay, how about that? Great. This morning's session on Euclid era challenges. Our first speaker will be Francis Bernardo. Thank you.
Yeah, thank you. So it's a great pleasure to have the opportunity to actually present the Euclid Mission and present more, I think importantly, the update on its expected performances and on the schedule. So as you know, the Euclid Mission is a Cosmic Vision 2007 program of the ESA. It's a result of the merging of two original proposals, Space and Dune, Italian and French proposals, so now it has been selected in 2011. And the consortium now comprises about 1,200 active members. More than 2,000 have been registered in the consortium. So this is just a matter of scale in terms of management. This is not an easy thing. It's Transplanckian. Yeah, I know. And so Yannick is the lead, the actual scientific lead of the mission. So as you know, Euclid is a mission dedicated to probe dark energy in gravitation at large scale, and this is as such complementary to Planck. As dark energy manifests itself in the low redshift universe, that is about redshift 1 and less. So it's all about mapping the large-scale structures of the universe to pin down departure from a lambda CDM if possible, and to explore the possibility of having non-standard gravitational gravity or non-standard energy content of the universe. So basically, the Euclid mission will comprise mainly the wide survey. So the wide survey is 15,000 square degree survey outside the galactic and ecliptic planes. It will contain about 12 billion sources, but about 1.5 billion sources will be used to measure weak lensing that you will have, so for which you will have good shape measurements, and for which you want to have photometric information, and this is all about cosmic shear measurements. We've heard throughout this week how important it is not only to have good shape measurements, but also for photometric redshifts. It also will provide spectroscopic redshifts for about 35 million sources, and that will help, and that will be the other, basically the other probe of large-scale structure, that is galaxy clustering. Besides, so Euclid wide surveys, there will be Euclid deep surveys, so 3 deep surveys actually that would be helpful in particular to calibrate all of these distribution in terms of redshift in particular. So basically the idea is try to pin down departure from standard gravity, and this is by different means. One is the expansion history of the universe, that is BAO, so the pinning down the BAO scale at large redshift through galaxy clustering. The growth of structure through galaxy clustering, so basically in redshift space distortion, so you have information on both velocity and density fields, and the idea is to be able to measure the growth rate of structures through that information. And the other probe is weak lensing. It's a major probe in terms of for the mission that we'll see in a moment. That will help measuring the evolution and the cosmic evolution of the power spectrum, of the density power spectrum in particular, and that be so a probe for departure from standard gravity. But it's not only that, it's the combination of the two is actually interesting on itself, because you have information, for instance, on how psi and phi behave, if they behave the same way or differently. So these are all of these probes are really designed to be able to check this kind of departure from standard gravity. As I was mentioned throughout the week, the main observables would be power spectra and extension of power spectra, but obviously Euclid would be useful to explore other effects such as galaxy cluster, so other probes, galaxy cluster, strong lensing, so clusters either from galaxy distribution or strong lensing, CMB cross correlation, and many other, of course, effects that you may want to explore. So so I was mentioning, basically is designed for this use. So so Euclid has two instruments, VIS and NISP. So VIS is an instrument for imaging in the visible band, and NISP in the infrared for photometry. So this is actually the NISP instrument here. This is a flight model, so the cold part of the flight model, which is already delivered now. And VIS is still under construction. So this is how it looks like. I come back a bit to the design of the telescope. So with these two instruments, NISP is this one, and VIS is actually different subsystems that are on different stages of delivery now. And with optical system, I say a word afterwards about its performances. So more precisely, this is the view of NISP of the two instruments in terms of bands and on capabilities. So this is really designed to do images, NISP to do photometry and spectroscopy through the rhythms. So the red rhythms will be used for the wide survey, and the blue and red for both for the deep as well. And this is the bands we will have access to in the infrared. In terms of field of view, this is how it looks like. If you compare, this is a Cosmos, well-known Cosmos survey. So this field of view of NISP and VIS, that will be, so images will be taken at the same time, right? Okay, I just don't want to go much into detail. This has been described many times. So what I want to stress is that really Euclid has been designed to control systematics. Euclid Mission, and specifically the Euclid telescope, has been designed to control systematics in terms of shape measurements. This is basically what you expect to have in terms of precisions, so of statistical errors, say, for the cosmic shift power spectrum, not tomographic, this is the full one. And so you really want to pin down this power spectrum at 1% level. So pinning down a power spectrum for a cosmic shear at 1% level, given the fact that galaxies are deformed at 1%, a couple of percent, means that you want to control systematics at 10 to the minus 4, right, in terms of shapes. So this put very, very strong constraints on the whole design of the telescope, and this is really what Euclid has been built for, or has been built for. In terms of photometric and spectroscopic redshift determination, well, you should think of Euclid as a global mission. It's not only what has been observed with the satellite, but it's also the complementary surveys that should help and that should contribute to the determination, accurate determination of the spectroscopic redshifts. So without these ground-based surveys, the goal of the mission won't be achieved. So what I'm going to present is basically an update from the Euclid Red Book in terms of performances. So measuring ellipticities with Euclid, as I said, this is one of the main goals. And the game is always the same. That is, you use stars as a way to measure the PSF. So basically what you want to measure is the PSF, so the point space function of the instrument, to deconvolve that from the measured galaxy shapes to have the exact, the true deformation of the galaxy. And then you use stars as PSF calibrators, and basically from nearby stars you measure, you infer the PSF for galaxies. And so the design of the instrument is based on this core 3 mirror design, and basically to be in the best position to control all contribution to the PSF going from the instruments. So this is working well. So we have now, maybe I switch that. So this is working well in the sense that we know more about the behavior of this system now. In particular, what is called the stop analysis for the structural thermal optical performance of the telescope, not only the telescope actually of the whole satellite, and just flash a few results. So what it is about is really a modeling of the whole satellite in terms of how the thermal variations are going to impact on the satellite. This is basically one of the main sources of systematics in terms of optical performances, because if you have any deformation, obviously it deforms your images. We're talking about 10⁻⁴, I remind you. And so if it would be a problem, right? So the result, and that was the reason the whole system was based on silicon carbide structure. And this is results. It's not yet the measurement of the whole thing. It has to be calibrated in flight, but this is basically very simple behavior. Basically, the telescope is breathing if you change the temperature. And so it's a simple change of basically the size of the optical bench is slightly moving. So this is kind of easy to model, and this is a good sign that the telescope is behaving in a good way, so to say. More worrisome is about the optical design as well. There was complex optical design with mirrors. So there are mirrors that, I mean, the standard 3 mirror of the quartz design, but there are flat mirrors to just to control the beam, but also to make these mirrors are used to define the bands, right? And you want the very sharp cutoff in between bands to be sure you have no leaks between different bands in order to analyze properly, once again, the flux for different sources, galaxies and stars. And the problems, one unforeseen problem arise with the, I don't see it here, the dichroic here. So the dichroic is used to separate the two beams, and it's a complex structure. And what turns out that because of the coating of this, it didn't behave exactly as expected. In particular, there is an expected wavefront error. This is what expected in terms of impact of this dichroic to the ellipticity changes, errors. So very simple lambda dependence, because it was for the V's channel, it's just reflection. But this is actually what it might look like. So a much more complicated lambda dependence. And this is now under investigation. And probably we will need to, or actually we are now designing, or Jérôme is actually designing an optical bench to actually model and calibrate this effect, so this chromatic effect. So this is the most, in terms of the design of the satellite, this is the most worrisome aspect that we're facing now. And so this optical bench that will be set in Lyon actually will, in principle, should be able to model accurately enough. This is yet an open question. Accurately enough this effect so that it doesn't impact on the PSF reconstruction. The difficulty is not so much there is a lambda dependence. The problem is that stars and galaxies do not have the same spectra. So when you want to measure the PSF from one to get the PSF from the other, you have to take that into account, and that's a difficulty. Okay, ongoing. I should say about one more thing about photometry and calibration of the photometric redshifts. Basically, you need extra surveys, so extra survey in particular for the wide survey, so that you have photometric surveys to help determine this photometric redshift, and also spectroscopic survey to calibrate them. So this is ongoing. Wow. And ongoing observation. Some large fraction of these of these data are now secured. We are still on some of them are still under discussion, but this is so on the way. I don't know how much time I have left. So already 15 minutes? Okay, so I go quick for the revisiting the Euclid top science requirements with the SPV exercise. This is something which is done internally. Basically, it's an update of the Red Book in terms of figure of merit and performances of the satellite. It's based on an effort, one of what's called IST forecast, so that was now closed, but led by Valeria, Tom, and Aya Sanchez. Basically, securing and the codes that have been used to compute the performances and you know, figure of merit of the mission. It's all based basically on linear physics plus ad hoc recipes for nonlinear effects. So this is basically computing what is the statistical power of the mission. It doesn't mean that we've proved that we can harness this statistical power. Right? So this is really what it's take then. So this is based on that you can compute basically what is the expected performances, and this is an update in the sense that it takes into account more precisely what is the number density of sources, what is the performance in terms of photometric redshift, and so on. So basically, this is done in terms of two numbers. One is called figure of merit, which is computed from joint precision on departure from a pure lambda dark energy, from a pure cosmological constant. And the other one is from the growth rate of the structures, that is whether it departs. So gamma, as you know, is an indicator of whether we visit standard general relativity. So gamma to be about 0.55, otherwise no. And so this is basically what it is about. And the Red Book promised a figure of merit about 400 and about 2% precision for gamma. And so the update is about more precisely how many galaxies you expect to have for galaxy clustering, given the depth of the survey. And so this is an update on what you expect to have in different models. So you see here different models 3, this is from Red Book, and now these two options are still open because we don't know exactly how many galaxies there will be. It's still not known. And so these two options will lead to, obviously, to different numbers in terms of figure of merit. And this is what you expect in terms of bin definition. So basically, the performances of the weak lensing probe is based not only, as I said, on chap measurements, of course, but on the fact that you are able to do multiple source planes, and you need to be able to define accurately this multiple source planes, and this is basically the performances we expect to have in terms of redshift distribution. And this is where we are. No, this is just the hypothesis. I won't go much in the details at this stage. This is where we are for galaxy clustering. So with the figure of merit here. So different options here in terms of whether you vary some parameters, whether you marginalize over some parameters that describe the redshift space distortions. This is a damping and damping scales, basically. But as you see, these are rather modest numbers, and most of the contribution is coming from weak lensing. So this is a figure of merit for weak lensing. So this is basically, so I'm pointing to these two numbers here. This is DR3 best, meaning that we have all the complementary data we need. The secure, meaning that we have all the complementary data we have now. We know we will have at DR3 release. So basically, this is what we get here. And what I want to point out is that this assumes that we can go up to Lmax of about 3,000 and 5,000, which means quite large wave numbers. So this is well beyond the linear regime. So what is at stake here is the understanding of these power spectra up to this scale. So now if you combine the two, indeed you reach this 400 number in about, well, for the nominal DR3, this is what you have, even if you are very pessimistic in terms of galaxy number densities. In terms of gamma, the performances are not so good, depending on the range of redshift you want to have, because at some point the redshift range was restricted so that you have good precision. Yeah, on the photometric redshifts, so leading to a restriction to this. But then the price you pay, that you diminish your precision in terms of gamma. So if you want to get back to this 2% level, you need to extend back to this redshift, even though the precision won't be so good on the deeper bin. So I'm about to finish. This is what I said, challenges in terms of the instrument I just described, in terms of acquiring systematically controlled power spectra or observations in a more general sense. One of equally challenging thing is actually to harness all of this information. As I said, we are now compared to Planck, where basically the physics was in the linear regime or slight extension of the linear regime through like lensing effect. Here we are really exploring the physics beyond the linear regime, and most of the data will be beyond the linear regime. And what's at stake here is having accurate predictions, well, meaning with control errors, right? So theory are good at proposing models, but not so good at giving the theoretical errors that are associated with. Identification of observables beyond power spectra, this has been discussed at length during this week, and computation of likelihood, all of that global data vector, whatever you put in, which will be very challenging. I insist then on the role of simulation in all of that, and within the Euclid consortium, a huge effort has been done, not only to build dedicated n-body simulation to start with, and then to be able to build mock catalogs, mock images, and so that the whole chain of analysis will be processed in a coherent way from a given cosmological simulation or set of simulations. So this is the first Flagship 1 and the Flagship 2 simulation is now on the way. I will finish with my last couple of minutes, I guess, with the schedule. So schedule launch is mid-2022. This is a hard date. We cannot go much further after that for some reasons. We're now in the process of delivery of the instruments. NISP is about to be delivered by the end of the year. These should be as well, maybe early next year. And then the completion of the flight model should go smoothly after that, hopefully. Meanwhile, we're actually working, as you guess, on the ground segment. So lunchtime, lunchtime 2022, meaning that, before I said, now an important step for the consortium is definition of the deep field. So now if these deep fields are now set and defined, and there are actually complementary observations already on the way or on the preparation on these deep fields. This is important for the whole community that these locations are now given, so that anyone can actually use this field, and the richer the observation on these fields, the better. The full survey is not fully defined, and still this is very something in preparation. So again, about the schedule. So as I said, so mid-2022 here, commissioning 3 months. And then the first, actually the quick release, Q1 will be after 14 months after. DR1, DR3, and DR4 will roll after that, and I guess we will be pretty busy analyzing the data. So it will be how it looks like. The mission will last, the nominal mission is 6 years. Extension is possible, but actually the instruments, in particular the VIS instruments and the CCDs, the performances are expected to decay in time due to cosmic rays, and you will have more and more defects in the CCDs that would diminish. That would diminish the performances. So we do not expect to have many times with 6 years. That's it. That's just to conclude. So far, Euclid has kept its promises in terms of potential performances, but also in terms of challenges as well. Thank you.
Okay, questions for Francis?
I think my question may be very naive. So when you measure the galaxy shape, the fact that you have projection effect.
You are, sorry?
Projection effect, because
yeah.
we are doing it on a 2D projected from 3D. How is that handled? How is that taken care of?
You mean?
What is the shape, actually?
When we measure galaxy shape, cosmic shear formation, yeah, so there is a broad kernel that describe where the lenses are, and so this is a degenerate information. So we don't know exactly where the lenses are. We can have some bit better information through tomographic effects. That is when you have multiple source planes. So the idea is for Euclid is basically to have about 10 such source planes for which you have good determination of where the sources are. And so this is what it is. That is, we won't have a 3D information. We have a slightly better than 2D, 2D plus information, but not 3D information on the lens distributions.
Okay.
I have a very naive question. You say that the variation of solar illumination, I guess,
of what?
Of thermal variations,
yeah.
Results in essentially breathing of the telescope, which is a monopole term. I would have assumed that with an anisotropic light, I would rather have at least a dipolar, the breathing would be a little bit different. And so I don't, why is it that this is getting thermally homogeneous immediately? I mean, because the source is anisotropic, right? So how come?
You mean the illumination from the sun?
Yes.
Yeah, so initially the performance were not so good. There was some effects through the arms that for the thrust, right?
Okay.
Okay, that would create some deformations that were not on spec, and the design has been slightly changed. So this is not a full analysis of the formation, right? But the main one is this monopole. And this is also due to the fact that this is silicon carbide structure, so very rigid.
So you are saying you're pushing on one end, but this is so rigid.
Yeah, yeah. So basically, this is what it is about, and this is thanks to the original design, and the fact that the whole spider, right, the whole stuff is in silicon carbide is really the key to that behavior. So the whole structure is the same material, right?
Okay.
And that was the point initially.
Do you think that Euclid will be able to probe any possible scale dependence in the growth rate?
In the growth rate, yeah, but this is, obviously this is at stake. But as you know, if there are scale dependence in the growth rate, it's probably in the risk regime when you are entering the nonlinear regime. So it'd be for k, well, 0.1 to point something.
Well, it
Sorry?
also come from modified gravity, the scale dependence.
Yeah, sure, but if you have information, I mean, The bulk of information will be in that K. And as I was saying, you can detect it provided that you are able to model precisely the nonlinear effect in that regime. And in particular, one key question is how to distinguish that from the effect of massive neutrinos, for instance, for which you also have K-dependent growth rate and time-dependent growth rate. So basically, this is all what it is about now, is to be able to pin down a specific effect like this and distinguish it from normal physics. Maybe I have a comment on that, a general comment. I didn't go into the challenges in terms of data analysis issues. Elena will speak after me. No, but I think that one thing is to build all the necessary tools to measure cosmological parameters. Another thing will be if we find that something non-standard is there, that is, it's not pure lambda, to convince ourselves and to convince the rest of the world that indeed we have detected something non-trivial and we have detected the new state of energy or matter. I think it will take a lot of effort to convince the rest of the world. It won't be just a chi-square in the end.
Right. Okay, so let's leave it there and thank Francis one more time.
Thank you.
So our next speaker is Elena Selentin from Leiden University.
And I can deny. And then you're happy. Yeah, thank you. Beginning. Yeah. All right.
Okay, our next speaker will be Olivier Doré.
Thank you. All right. Good morning, everyone. So let me start by thanking the organizers for inviting me here, especially Sylvia and François. I'm very happy to be here. I really enjoyed the conference a lot. And of course, it's always special to be back here. So clearly, this slide shows one thing that I have much less integrity than when, because I was given a title, but I didn't even think twice about changing it to what I thought it should be for this talk. So that's the title I came up with. And I think I was tasked with some kind of large-scale structure review for the coming decade. So I cannot cover it all, but I will cover a few essential surveys of the next decade and discuss the synergies between these surveys. And this is a work I will present. Much of it has been obtained in collaboration also with the Spheric science team and WFIRST also science team, cosmology science team, and I want to acknowledge with two members, Elisabeth Krause in the audience and also Tzu Cheng. Okay, so as we all know, clickers don't work. So as we all know, the next generation of surveys is really is motivated by solving the mystery of dark energy. It's really trying to figure out what the nature of dark energy is. And so to start, I figure it would be a good thing to start with where we stand regarding constraints on the dark energy equation of state. And so this plan is extracted from the Planck latest cosmological paper. And you see the constraint on the equation of state, evolution, WA, W0. And so you see several things here. You see first the Planck constraint here, Planck plus BAO on supernovae, Planck plus BAO, RSD, and weak lensing. And clearly, you see one thing we keep hearing throughout this conference is clearly there is strong complementarity with multiple probe, and all the measurements we have are consistent with the cosmological constant, which would be here. So given this plot, it's important to see where we want to go, and where we want to go would be more or less this contour here. It's not a rigorous forecast, but it's order magnitude of the constraint we want to obtain with the next generation of surveys. And so this goal motivated very ambitious surveys throughout the world, and so the community is organizing very organized, massive effort, and I will list them now in chronological order and discuss them very quickly. First one, it will be the DAISY survey, and DAISY is a highly multiplex spectrograph, put on a 4-meter Maillard telescope at Kitt Peaks, and it will deliver exquisite constraint on the expansion rate of the universe through dA on H from a redshift of 0.05 to all the way to redshift 2 using lambda and alpha. And so we can expect exquisite constraint coming from BAO on redshift space distortion. The next one will be, of course, LSST. Everybody knows about it. LSST will be a tremendous imaging survey. We will, from the image every 3 nights, the full southern hemisphere, and will, in a process, will provide exquisite weak lensing, supernovae, and BAO with photometric redshift measurement. Okay, and this will start in, the science survey should start in 2021 or 2022. Okay, the next one is the Euclid. We just heard a great talk from Elena and Francis, so I won't discuss it, but again, just for the context, it's obvious that Euclid will deliver groundbreaking weak lensing measurement, BAO, and also redshift space distortion. The next one is a new game in town. It's a SphereX mission, and it's important to realize that SphereX is not optimized for dark energy, but will still, nevertheless, provide a very compelling galaxy clustering survey from which we can infer important constraint. And in particular, SphereX is optimized to measure very reliably the large-scale clustering of galaxies to measure primordial non-Gaussianity. And finally, the last one, surveys, which will come in mid-20. So SphereX will launch in 2023. WFIRST will launch in 2025 and will provide extremely high-quality weak lensing measurement, BAO, redshift space distortion, and also supernovae. So I will show my own personal bias and also discuss a survey which have not been discussed much in this conference, and I will focus my talk on these 2 surveys. And I will ignore the CMB, future generation of CMB measurement, although we heard yesterday and we'll hear later from Julian that clearly CMB surveys are becoming more and more large-scale structure survey. And I will also not discuss intensity mapping surveys, and because Phil will discuss that this afternoon. Okay, so WFIRST quickly. So WFIRST is the next NASA flagship mission. So the flagship mission is the largest class in astrophysics enabled by NASA, and that's a class that really enabled major observatories like Hubble, Chandra, Compton, and is also JWST, who is about to launch. And so the next one will be WFIRST, who is scheduled to launch in 2025. The proper way to think about WFIRST is really Hubble-like quality. It's more or less the same size, same mirror as Hubble, but there's a much wider field of view. So it means it will allow very fast survey. And so what you can expect from WFIRST is really Hubble quality images over 1,000 square degrees, right? So it's really, you can imagine a Hubble deep field, but over 1,000 square degrees. And that's really what WFIRST will deliver. And with this, WFIRST is optimized to deliver this kind of constraint is motivated by ambitious program on dark energy, exoplanet, and also general wide field survey astronomy. 2 instruments are scheduled on WFIRST. The first one is the wide field instrument, so will enable imaging and spectroscopic measurement over 1,000 square degrees between 0.7 with imaging between 0.7 and 2 micron, and spectroscopy between 1 and 1.93 micron, and it's so 6 filters in imaging, 1 grism, 1 prism. At the same time, there is also a coronagraph. I won't discuss it more, but the coronagraph, the goal is really a technology demonstrator to enable the next generation of exoplanet direct imaging. So it's really, so this coronagraph will enable direct imaging of some planet, and is really to lay the groundwork for the next generation of mission who will directly map exo-Earth. Okay, so WFIRST is 3 surveys, an experiment, and an observatory. So the mission is scheduled to last 5 years currently, and it's 3 surveys will be 2 years, and that's, I have to say, all this is notional. This is all the surveys will be frozen a couple of years from now, but that's what we define to define all the requirements to define the mission. So the first survey will be a 2-year survey called a high latitude survey that will provide, which is the main cosmological survey, and that will provide high quality imaging and spectroscopy over about 2,000 square degrees. It will be intertwined with a 6-month supernovae survey, and it's really a collection of fields that are repeated regularly with some very well-defined cadence. And finally, it will also dedicate, of these 5 years, 1 year will be dedicated to repeated galactic bulge observation for microlensing studies. The experiment I just mentioned is really the coronagraph, which is really technological development. It's an experiment. And finally, it's an observatory because 25% of the time will be guest observer time. It means you can, just like Hubble, you can write a proposal, propose to observe your favorite field, conduct your favorite survey, and you'll be given the data. And one important fact to know also about WFIRST is the fact that all the data will be public within a few days after they're taken. So it means there is no preparatory time. So all the data, level 2, so calibrated images will be delivered very quickly. And that's something NASA is very committed to, so it will happen. OK, now SphereX. So SphereX is a very different class of mission. It's a latest astrophysics mission selected by NASA. And this time it belongs to the Explorer class, a medium-sized Explorer class. And it's a class we know very well, which has been very successful in astrophysics. It's a class that enables WMAP, FUSE, WISE, and more recently, TESS, the exoplanet survey, who is currently operating. So it has been, the specificity of this class is that it's competed. It means you write proposal, and you compete against different concepts, and you are ultimately selected, and it's PI-led. Okay? And so SphereX, the one thing to remember about SphereX is really the data set that SphereX will deliver. So the data set will be for every 6.6 arcsecond pixel of the sky will provide a spectra, low resolution spectra between of about 40, between 0.75 and 3.8 micron, and at a spectral resolution of 120, between 3.8 and 5 micron. Okay, so it's for every pixel of the sky, we will deliver a spectra. Okay, so it's 13 billion spectra, if you want. It's low resolution spectroscopy, so you can think of it also as fine band photometry, in which case we have 96 bands. So it means this data set will be 96 full sky maps of 6 arcsecond resolution. So that's really the data set that will be delivered. Clearly, with this kind of data, so on the desk theory, what you see here is a magnitude AB, predicted magnitude AB at 5 sigma as a function of wavelengths. Each black dot here corresponds to the sensitivity expected per frequency resolution. Okay, and so this corresponds to the whole sky survey, and the two curves correspond to the different noise model. In practice, will be hopefully somewhere in between. And these curves correspond to the deep field survey. We'll conduct 2 deep field, about 100 square degree each, and this is the expected sensitivity. So in terms of, over the full sky, per frequency element will be at about 19.5 magnitude. And it's, as a reference point, you see here 2 mass, so clearly it's a big improvement over 2 mass. But you see here WISE, depth over the wideband W1, W2. You see that per individual frequency element, we are as deep as WISE. It means that we will have a spectra for every single WISE sources. Okay? And then for reference, you see Pan-STAR here, which we will use in our photometry for Redshift calibration. Okay, so clearly, again, we will have a spectra for every pixel of the sky, so we'll have spectra for all kind of astronomical objects, and we forecast 1.4 billion sources overall, several hundred millions of galaxies with a good redshift accuracy, which is better than sigma, 10% in terms of sigma z over 1 plus z, and 100 million of stars, 400 brown dwarfs. It's very good at finding, in the infrared, actually very good at finding spectra for high redshift quasars. We'll have a spectra for all the known asteroids and comets. And also, we'll be able to do very diffuse maps, for example, of PA edge, H1 or H2. So it's going to be a very high legacy data set, obviously. And it's opening up a new corner, if you want, in parameter space, so it's prone to discover new kind of objects. But I said, and so how we do it? We really do it by this very simple design. It's an Explorer, so it has to be simple, and we are starting to build it next year. And so what it is, it's just small mission, so the height is like just my height, actually 1.98 meters, and it's the key feature, so it's passively cool. And you can recognize, aficionados will recognize here these V-grooves, which are inspired from the Planck V-grooves, the 3 Planck V-grooves. And it's a small mirror, so the effective aperture is 20 centimeter. But it compensates for this small size by the very wide field of view, so that the étendue remains very large. And so the field of view is 38 square degrees. So that's the number one characteristic. The second characteristic, which is we conduct a spectroscopic survey without a spectrograph. And the way we do it is through this, what is called linearly varying filters, and linearly varying filters are interferometric filters whose transmission vary with position. So we put this filter in front of the detectors, and it means that each row of the detectors see a slightly different colors. And you can understand right away is that by then stepping the focal plane throughout the sky, we can reconstruct the spectra of every source of sky. We don't collect any spectra instantaneously, but we reconstruct the spectra by combining several exposures. And so on the advantage, you can see that it's a very simple design. It's a very simple way of operating, which makes it perfect for space mission. And it's also, in terms of heritage, it's really, it's a way to conduct a spectroscopic survey like you would conduct an imaging survey. And it's something the community has learned to do throughout the years. And so we can do that. We can apply all these techniques which have been developed by multiple surveys, but this time to conduct a spectroscopic survey. I mentioned before that SpherX is really optimized to measure large-scale structure survey, to measure galaxy clustering on large scale reliably, and it's really optimized to measure, in particular to measure FNL. And so here are our expected constraints on the running of the spectral index, prominal and Gaussianity. So in this plot, in the background, as we heard from Raphael yesterday and others, so single field inflation model will have, most of them have a very small FNL, so they will lie on this line here, okay? Slow roll inflation model will have a very small running of the spectral index, so they will lie on this ground. On SpherX, in the background, you see a distribution of likely multi-field inflation model after Planck, and the color coding correspond roughly to some kind of density in some model space. And the blue contours correspond to the current constraint from Planck. In yellow, you see here the constraint expected from the SpherX power spectrum measurement. In red, in orange, the constraint expected from the bispectrum measurement, and in red, the combination between them. And so roughly, we are forecasting sigma FNL of 0.5, including systematics. So that's our goal. Okay. And so the motivation, of course, is should be able to distinguish if inflation involves multiple fields, we should be able to see it. Okay? That's the number one goal. So now let's come back to the dark energy surveys and not talk about SpherX anymore, but the very large scale dark energy survey. And I want to show you a few numbers. So I fully realize big tables are a big no-no for talks, but nevertheless, I want to show for reference a few numbers. So what you see here, LSST, W1st, Euclid, DAISY, all big mirrors. You see that W1st, by design, decided to cover a smaller area, but to go deeper, and it's really motivated by systematic control. And one thing also, you see that in terms of W1st will sample the PSF reasonably well, less well than LSST, but better than Euclid. So in terms of photometric survey, we will conduct a full, for the survey I mentioned before, it will be a 4-band for W1st and 6-band versus 6-band and 4-band for Euclid. But in terms of shape measurement for galaxy, we will measure galaxies by design with high signal to noise over 3 bands versus 2 bands. This is a mistake. It should be 2 bands for LSST and 1 band for Euclid, with a high multiple pass to allow redundancy and cross-check. For supernovae, W1st is designed to complement LSST, and we expect between 2,700 and 20,000 supernovae all the way to Redshift 2 with prism spectroscopy to get the Redshift and spectra. And finally, in terms of spectroscopic survey, so for this, we have ambitious ground-based effort. We stopped at 1 micron because of the atmosphere, which is DAISY. And then we have Euclid, which goes all the way to 1.85 micron. And W1st was designed to complement Euclid, so it'll go a little redder to have a spectra goes to a higher redshift. And W1st being deeper will also have not only H alpha, but will also have a substantial O3 sample all the way to redshift 2.8, which will allow multi-tracer studies, etc. Okay, in terms of visibility, in terms of sensitivity, you see here the 5 sigma point source sensitivity as a function of wavelengths. Green, you see the full LSST depth. In red, the W1st depth, and you see that they are clearly well matched by construction. So it's W1st will complement LSST over in the infrared, and then you see here the wide Euclid band, which is used for shape measurement, on other bands which are used for photometry. And so you see there are different solutions to really going after different way to optimize the survey. And I would say Euclid defined just to maximize statistical errors by going a little less deep, but covering much larger area. And W1st decided to go deeper, but over a smaller area to control systematic better. In terms of this naturally translates into different number density. Here you see the predicted number density for first in blue, and then the subsample that will be seen also by Euclid. And you see that we have more sources going to higher redshift, which is expected because we are deeper. And so, okay, so that's for imaging survey. Not for spectroscopic survey. That's a natural way to compare surveys, really to look at the effective volume. So effective volume, so it's trying to capture the number of modes a survey can measure. Number of modes is driven not only by the cosmological volume it's looking at, but also how well this measured sample. It means how the importance of the short noise. So you have this effective volume captures the physical volume and the short noise. And you see here the first expected first effective volume as a function of redshift. You see the Euclid here, which is larger because of mostly the larger physical volume. And you see here expected DAISY from the ground doesn't show the Lyman alpha constraint going to higher redshift. And you see that here, this spin curve, and it should stop really here, it should not have extended here, but the spin curve corresponds to the spherex sample with high redshift accuracy. So spherex has all kind of the accuracy will depend on object. And so we have a high redshift accuracy sample, which is a redshift accuracy better than 0.3%, which is what you need to do BAO or cosmology from the power spectrum. And so we'll do very well all the way to 0.8 or so, at which point we don't have any more sources. On the other hand, if you want to measure the FNL on large scales, you would use different different K in this formula, so you don't care about the same scale, so you can use a sample with lower redshift accuracy, and in which case you have obtain the red curve here, and you see that we maximize cosmic variance all the way to 1.5 or so. And that means that we really extract all the information on FNL, which can be extracted using the power spectra, all the way to redshift 1.5. And that's really the overall motivation. Okay, so now we are really, I mean, the list I showed is quite spectacular, and so the next decade we have really a collection of 5 major surveys. So, I mean, when you think of it, it's really remarkable. And I think we are really in a situation where the whole is greater than sum of its parts. So it means that none of the survey there will be very, very strong benefit from strong collaboration across surveys. And the first thing that will happen the next decade is that there will be multiple cosmological probes within survey or across survey, which will enable robust physical interpretation. We can measure the growth, we can measure the various distances, and we can measure each of them in different ways. So that will be a lot of cross-check, and that will enable, it will be really the decade of multi-probe analysis, and that will enable, again, really robustness in interpretation. Also, multiple surveys will enable, and Elizabeth mentioned that yesterday, will enable important and critical cross-check. And one thing we learned clearly from in the CMB community over the last decade is that it's very important to cross-check all measurement with multiple survey. A new insight on the nature of dark, it means that any new insight we will gain on the nature of dark energy will be thoroughly cross-validated, and that's clearly very important. Finally, it's also very obvious that joint analysis will have multiple benefits. We have systematic control, as Elizabeth will say, and we also have novel cosmological in signal. And it's important I think this fact has been fully embraced by the community, and there are already a lot of cross-planning activities, for example, most recently on a deep field, which are jointly planned across all these surveys. And clearly, if you are doing it, this will be the decade of MOUs. Okay. A few examples for LSST and WFIRST of kind of synergies we are expecting. So LSST, WFIRST by design does not cover the Balmer break at 4,000 angstrom. So WFIRST needs LSST for photo Z, right? And that's by design. There will be strong cross-correlation between the spectroscopic sample and the LSST sample, which will be very valuable, especially at high redshift to calibrate photometric redshift. And also for using WFIRST Euclid versus LSST, clearly the PSF in space will be much better measure, much more stable, which will enable the validation of LSST shape measurement, and that's really will be very important. An example, also a very strong synergy, which I think is going to be really worrisome but powerful, is the issue of blending that Elizabeth mentioned yesterday. So what you see here is simulation of a few images for LSST, single visit, LSST full days after 400 visits after 10 years, Euclid and WFIRST. And you see after 10 years, the green curve here corresponds to the isophotes in this picture. So you see two extended sources, okay? But if you look with W first or Euclid to some extent, you see really there are these sources are blended, and the blue curve corresponds to the isophotes coming from W first. And you see there will be actually 5 sources. And that's really not a particular case. Actually, it is expected, it's based on, for example, the HSC measurement, that the large majority of the sources in LSST at full depth will be blended. So we have to find a way to handle that. And when a blending is an important issue, it biases not only your shape measurement, but it also biases your photo Z measurement. Now that's really, so it's really for high precision cosmological lensing measurement, that's really a major issue. So that's an example where the combination of LSST and then Euclid and W first will really be critical. And an important point to make here also is that this point clearly shows that this cannot be done at the catalog level, right? It's not enough to combine catalogs. To solve this problem, you will really have to go at the image level and somehow jointly analyze this. So and that's an important task, mostly unfunded, and which will be really critical. I'll skip this. And just a few, just to finish, I want to highlight a few synergies also between Euclid, W first, and SphereX, which are, again, a very different class of mission, but nevertheless have very strong synergy. In cosmology, clearly SphereX cover the low redshift universe, which would naturally complement a deeper Euclid and W first. SphereX should be able to build a very high reliable extinction map because of the spectral information over the full sky. The stacking of faint isolated SphereX can really produce representative of SEDs. And using the deep field, we can really, combining SphereX and Euclid and the W first, we can really, it will help calibrate photometric redshift. I think one of the big, one of the big things that SphereX will deliver to the community is a calibration solution throughout the sky. So SphereX is designed with a high redundancy, like a CMB experiment. So there is a field we observe. We have 2 fields at the north and south ecliptic pole that we observe every orbit every 96 minutes. And so we'll be able to have a very stable and interlocked, if you want, calibration solution, which will help us find a very good calibration solution throughout the full sky. And to give you an idea of the magnitude we need to measure the FNL signal we're after, we are talking about millimag or less calibration throughout the full sky, right? Which is something which is very ambitious, has not been done, and it's not only on per exposure, it's really coherently throughout the sky. And that's when we do that, then we can pass that on directly to Euclid, and Euclid can use that as a reference frame to calibrate and tie up its calibration, for example. So I think that will be extremely powerful synergies. So, okay, I will stop here, and I think so. That's my conclusion is that the whole CosmoGold is greater than the sum of its parts, and clearly the coming decade is going to be transformative. We have multiple groundbreaking surveys being planned that will enable multiple multiple joint analysis and cross analysis, which will be important for systematic and also robust physical information. And so I think the key question is that at the end of the day, scientific discoveries are guaranteed, and for me, the open question is really how fundamental they will be. Okay, thank you very much.
Okay, questions for Olivier?
Yeah, you were speaking about the problem of blending and,
right.
and with this image of Euclid
right.
and LSST and so on. So now if you superpose sphere X, pixel will be much larger, right?
Oh, no, yeah, sphere X is 6 axion pixels, so sphere X would be, that would be 1 sphere X pixel. So that would, yeah.
Yeah, so in terms of now spectroscopy of these sources, you
right.
can you deblend them? Can you see that you have superposition different sources or not?
Right, so we do see that, and so our plan is actually we won't discover sources. So that's something I didn't have time to discuss. Because of this blending issue, we cannot discover reliably sources. But what we do is that we use all the sources which are already known from Pan-STAR and will be used for LSST. And we do force photometry on these sources. And when there are several sources within a pixel, more than 2, clearly we'll discard this pixel. So it will be a little hole in our survey, and that's fine. But it's not, unless it will be less than 10% of the pixel, according to our simulation. But so, because of this large pixel, really, it would be, if we don't have any match in the optical or in a higher resolution sample for these sources, it would be very hard for SphereX to figure out what it is. So.
And at the depths of the wide field surveys of Euclid, you would have only a fraction. I don't know. Maybe we should talk later.
Yeah.
So to this point, I think that can highlight the complementarity as well. I mean, for example, you could imagine using a Euclid-selected SphereX survey, for example. I mean, by cross-correlating between between these different missions, I think that's a very strong point, actually.
That's right, absolutely, that's right. And if you can select, if you select the isolated sources in Euclid, then you can really, maybe for the very faint one, magnitude 24, you won't get them. But if you, so actually something we wrote in this paper with Nikhil Padmanabhan I referred to, is that actually if you, and I'm totally ignore your I'm not letting you ask questions, sorry. And that if you, what we showed is that if you, there will be so many sources in LSST or Euclid, and if you restrict yourself to a very small area in a color space, and you make the assumption that the SCDs, there's only 1 or 2 class of objects or 1 or 2 SCDs, and you stack in SphereX, then you can reconstruct the SCDs on the end of Z, which should be actually, I think, should work pretty well.
So maybe I should ask this in the coffee break, but I have to ask, is there any chance that the mirror size could increase a little bit?
That's always
Is there any chance the mirror could be made a bit bigger?
Not at this point, no. And we really looked hard at it, and it's not. At this point, we are not. Yeah, we tried and we really simulate, and it's really an important trade space. So we are not resolution limited. We're actually sensitivity limited. So ultimately, SphereX will be photon noise limited on most bands, but the way we could gain would be by spending more time on a given part of the sky. And so we're really not sensitivity limited and not resolution limited. So there is no gain. We decided there was no 20 centimeter effective aperture was more or less the optimal size for us, given our constraints. So we won't increase the size. Yeah.
Sensitivity limited on the base mission, but given the history of NASA extending missions,
right.
It seems a shame to.
Yeah. So I'm not sure if we let's say if we extend to 5 years with a noise level expected there, if this trade is still valid. But I think at this point in the process, it would be really hard to change the mirror size already. Yeah. So it's, I mean, we're launching in 2023, so it's coming quick. Yeah.
Any further questions? Okay, well, let's thank Olivier one more time.
Thank you.
And all of our speakers for the great session this morning. Any announcements from the organizers? Okay, so we reconvene at 11 o'clock.
maybe it's at the bottom.
Testing.
No, the bottom, but perhaps. So, yes. Okay. Yes, I think so.
Okay, continuing our session on Euclid era challenges, our next speaker will be Chen-An Lin.
So, hiya, I think the microphone works. So thanks for being here, thanks for staying awake, and thanks for organizers to have me here. After 3 talks in the morning talking about the future surveys, Euclid, and topic first, I'll pull the timeline back to the current time, and I'll talk about a systematic effect that has not yet been studied, which can be useful for the future. So my name is Link, INC, and I'm from the University of Edinburgh, and I'll talk about the impacts of variable depth on the weak lensing covariance. Well, first, lensers don't necessarily study only the lensing. So this is a very good example. If we look at the Galaxy catalog, then we can extract at least 2 pieces of information. So the first one is a position, it's the biased tracer of matter density, and the other one is the galaxy shapes, which can be interpreted as a noise tracer of the projected matters. So we know that these 2 quantities, they correlate to each other, and if we want to extract the cosmological information, we can compute the 3 different correlations. So first, position, that's just the galaxy clustering, and if we correlate position with the shapes, that becomes what we call the galaxy-galaxy lensing. And finally, if we correlate both galaxy shapes together, that gives the cosmic shear. So we usually use these different samples to note them. So W, gamma T, psi plus, psi minus. But knowing that there actually exist different forms, for example, for the galaxy-galaxy lensing, we can transform that into the delta sigma, the mass profile, and then cosmic shears can be interpreted also by, for example, aperture mass or the Kosebe's, as Marika mentioned on Tuesday's talks. So this is the state of the art. Left-hand side, kilodegree survey, right-hand side, dark energy survey. So you have this KV KISS 450 result, and with this year 1 result. I think if you check the yellow of the left and the green of the right, that's the cosmic shear. If you check the blue of the right plus the red of the, blue of the left, red of the right, it's very confusing. That's the galaxy clustering plus the galaxy-galaxy lensing, and then if you combine everything together, it's a green contour here and a blue contour here. The take-home message is that by combining all 3 probes, you get a better constraint. So this is something which is relatively easy to achieve, so we have to do that if we manage to. So what does it mean, this, like, if we manage to? This is actually the systematics. So thanks to Elizabeth's talk on Thursday, yesterday, we actually all looked through a lot of systematics. So here, I will just remind you once again, one of the most important things is the redshift distribution. And so if you miss Hendrik's talk on Tuesday, he mentioned this plot. I think this is a very good illustration. By using different photometric redshift estimation methods, you can have quite different results, which varies between like 0.6 and minus 0.8 sigmas. So that's a very tricky thing that we need to deal with. And then also we have intrinsic alignments. So yesterday, Maria Cristina talks about the modeling, especially in the case of the magnitude limited samples, and look at the behaviors of the different satellite galaxies. The underlying message is that if we manage to understand this better, we can propose a better model. And so when we include that into a cosmological analysis, we can reduce the error bars and reduce the bias. And of course, there are some other things that we have mentioned in this week. So for example, the shear measurements, there are some intrinsic bias related to the method. We need to correct them. The galaxy bias here is actually less relevant to the cosmic shear, but if we want to include the galaxy-galaxy lensing and the galaxy clustering, these are very important things. If we can do it better, we prefer to go to a nonlinear scale. These are not the all. So there's a very important factor which is called baryon effect. This is actually a problem which can be seen from both sides. So you can say that I don't want to cut my scales. I want to understand and extract the cosmological information from very small scales. In this case, I need to have a proper baryon model. But you can think it the other way around. So you can say, okay, I don't have a trust baryon model. So to be conservative, I want to cut my small scales. At least I'm safe, right? So this is a problem of whether modeling a baryon or scale cuts. And this plot from Marika's cut on Tuesday is a very, very good illustration. You can see the integrand, or basically the weight function, the window function of the different observables, in this case psi minus, in this case psi plus. And you can see that it depends on it gives you a correspondence between the scales of your observables and the scales of your underlying physics. And so it can give you some indication, some justification for scale talks. And then there's another effect, what I call a survey effect, I'll detail later, which has not been studied yet. And of course, there are some other things that we might need to include in the future. So before going to the survey effect, let me talk about the covariance. Nowadays, we're still in, at least at the current stage, we still use a very conventional approach, which is likelihood analysis, and we also assume that the likelihood is Gaussian. Now, Florent Leclerc, for example, yesterday he talked about a likelihood-free inference method, which sounds very promising for the future, but now we have checked on the likelihood, and we believe that the likelihood is quite Gaussian, and so far we stick to this approach. In this way, then the covariance becomes very important, because that gives you directly how large your contour is. So there are usually 3 ways to estimate that. Estimation from the data, analytical formalism, and then embodied simulations. They have both pros and cons. So first, estimation from the data, some people will say that, yeah, in this case, we do need to assume any input cosmological parameters. But the problem is that if you do with a jackknife or bootstrap, and if your subsamples, they are actually highly correlated, it's a very dangerous way to do. And this can be the case for correlation functions, so I will argue that this is quite risky. And then analytical formalism, you can say that I know my physics, I know my baryons, or I know my signal, I know my noise, I just put them together, I can compute that analytically, and that's my covariance. Well, the problem is that you usually don't know the survey effect with some equations at a likelihood level. So that's a challenge things to do. And this is later what I'm going to dig in. So some people will say, okay, analytical formalism, they have some challenges. Why not just run embodied simulations? And I believe that's the Euclid approach, correct me if I'm wrong. But there's still some problem, right? Embodied simulations, they are limited on large scales by the box size. They're limited on small scales by the mass resolution. And then if we can correct the large scale by analytical approach, small scales try to ignore that with some scale cuts, we still need to face to the limited computational resources. That means that it takes time. So none of the approach is perfect, and I think depends on the survey specificities, we use different ways. Okay, so now let me take this because this is what kids and devs do currently, and I will take a look at the survey effects. So what are the survey effects I'm talking about here? It's actually very straightforward, all this talk. So the first thing is just very simple, mass geometry. So here I show you the footprint of balls and kids. So you have the overlapping region shown in yellow. And I want to do the 3 times 2-point analysis. That means that I want to know the cross correlations between different props. I want to know the correlations between the correlations, right? So you can ask this question, okay, I have all this purple plus yellow area of the galaxy clustering, and then I have this orange plus yellow area of the cosmic shears. What's the correlation between them? Well, it's actually very difficult to do analytically. The second thing is that you can see that there are holes in the mask. Okay, so that means that your pair count will be affected. The pair count will affect directly your noise signal, your noise term in the covariance. And if your extent is quite regular, you can estimate that more or less analytically. But if you have many, many holes, you don't know how your pair counts are affected for different scales. So that's why the analytical model struggles. And next one is what we call the variable depth. So these 3 plots are the preliminary measurement from the KISS 1000 data. So let's just focus on some of this left-hand side panel. These are the redshift distributions from the different pointings. Okay, so if we look at the pointings of the skies, we know that the weather conditions, they are not all the same. So that gives you a different depth, different Rband magnitude, Rband limit magnitude of your object. So if we beams them, into 10 different beams, and then we compute the average distribution, you can see that there's a shift. It's very natural because, the better seen, the higher the depth, the fainter object you can observe, and you'll have more high-redshift galaxies. So that shifts your N of Z. And of course, if you see this internal variation already between the pointings, increase your covariance. And secondly, if you look at the N effective, so that is the Galaxy knowledge number densities, it's also very natural. So you go to a deeper field, you have more objects, increase your densities. And then we have a more complex structures for the, this is a shape noise, but it's, you can see that variations. It will want to know how it impacts the weak-density covariance. So that is basically the main question. What's the impact of the survey footprint on the weak-density covariance? If it's small, then we may be able to ignore it. But if it's large, then another question comes, how do we model it? So that's the question I would like to answer. So in this case, we have to use the simulations. And instead of using embodied simulations, we use the fast simulations. So this is a Flask. This is open software written by this group. So it provides you the fast Gaussian and log-normal simulation. You only need to use the Boltzmann code to compute the power spectrum and then do the Gaussian random field. So this is a full sky in a Hillpix math Gaussian random field. If you want to do the log-normal fields, it's a bit more complicated. You need to do some transformation, but the solution exists, and you may need to regularize. But in the end, what we get is the full sky maps at a single redshift, and you can do it for different redshift slices. So this is a very, once again, very straightforward. You compute the CLs, you generate the density and the lensing maps, and then you sample the galaxies, Poisson sampling, assign the lensing signals, and you apply the survey's characteristics, mask, effective densities, and also the N of Z. And then after that, you compute the correlation functions. And we do this exercise for different cases, simple mask complex max, or uniform depth, variable depth, and we just compare them. It's very straightforward. So first, we have this tool. We want to validate that. Now let's compare with theory. So dots are from the MOX, and the lines are from the theory. We have the Galaxy clustering, Galaxy has the lensing, and then cosmic shear, psi plus, psi minus. As you can see, there are like two things apart from this 90 offset and the small scale disagreement due to resolutions. Everything else works very well. If you want to ask questions, you can come back to it. I'll come back to that. So then the mean is fine. Now let's compare the covariance. So we have the mock covariance compared to the theory covariance. These are the diagonal terms. You can see that they agree very well within 10% level. It's actually 10% for the very extreme beams. Most of them will agree within the 5% levels. Right-hand side, you have the off-diagonal terms. So this time we look at the correlation coefficients, upper triangle for theory, lower triangle for MOX. You see that they're actually pretty similar. Let me help you a bit. So this is zoom-in version of the plot. MOX, theory, MOX, oops. It doesn't really work. Theory. So you can see that only here, maybe it's not very clear, but you have some like tiny, very low level, percent level fluctuations due to the stochasticity of the MOX, but otherwise, all the other terms, they agree pretty well. So let me move to the preliminary results. I only have a very simple result to show you. Sorry for that. But it's actually more complex than you think. I need more time investment. So this is the first one. We have this configuration. Now, one question we can ask, if the overlapping area is so small, can we ignore some of the cross correlations? Because that will make our life much, much easier. So the answer is yes. And if you look at just these two black blocks, so this is the cross correlations between Galaxy clusterings with Galaxy lensing plus cosmic shear. And you can look at this. This is the correlation coefficients. They are almost white. Now, if you take a cut, a threshold of 10% plus and minus 10%, this is what we have. So we have some red spot here, but in general, it's very white, and it's very, the correlation is very low. Of course, zero correlation doesn't imply the independence. but at least it provides a strong justification to separate the likelihood and analyze them separately. So this is my final result. Now we look at the effect of a variable depth. So you have the quantity by assuming a uniform depth compared to a reality, okay? So this is a fractional difference of a uniform over the variable. And this is the fractional difference on mean, fractional distance on the diagonal terms. You can see that on mean, it's very mild, only 1% level, okay? But on the covariance, it's roughly a 5% effect. And this is a standard deviation, right? So if you really want to look at the terms on the covariance, that's 10%. Fortunately, it tells us that this is quite constant. So 10% of the covariance for case-like survey is at the borderline. We will model it, of course, but it might be okay to say that it's negligible. For the future surveys, it's less obvious then. So this is my summary. There are only like very few take-home messages. Variable depth can affect your weak lensing covariance, and for case-like survey, it's 1% on mean, 5% on the covariance. And then might be significant for future optical surveys. And then here are my collaborators. I work for this project in the KIDS collaboration framework. I work mainly with Benjamin Joachimi, but also with some of other members with Marika here, of course. My name is Link, and thank you for your attention.
Okay, questions for Link?
Thank you. So in comparison to the numbers that I just showed in my talk, when you have a 5% uncertainty on the covariance at KIDS resolution, I can shift parameters. So I think you should put it in. And you should put it in as
we will put it in,
yes,
for sure.
But in the end, you also said it's maybe negligible for current surveys,
okay.
So I don't think so.
The problem is that for the current state-of-the-art covariance comparisons, between different codes, we can go up to several % of the differences. So that's why I say that. But
like the problem
of course,
needs a solution then.
No, I agree.
Other questions?
A question I had is, you try to treat differently the small holes that you showed and the overall footprint of the survey, and to check whether those two different issues would have different signatures in the error in the covariance, and could be modeled with in different ways.
Yes. So we have actually a various different ideas. So to model this, right? To model this. So this is the full covariance with signal term, mixed term, noise term. And in signal terms, actually, you can break down, right? You have Gaussian term, non-Gaussian terms, and supersample terms. Ideally, we want to model everything. But the result I didn't show is that actually, sometimes they don't really vary, in the same way. So you maybe have your scale dependence. Sometimes in the psi plus and psi minus, they don't have the same behaviors. And actually, cosmic shear altogether is actually a mixture of the psi plus and psi minus. So if we can come up with a simple model, then we'll do it. Otherwise, if we can, take a step back, if it's too difficult to model each term, but by combining we have a simple model, then we might do that. But it's also possible that with the realistic footprints, with realistic depths, we have a very, very complex behaviors on the covariances. Now in this, we might just have to take a simulations and run many, for example, 10,000s, 20,000s, and estimate covariance from a simulation. That might be the solution that we have to do. We don't know the answer yet, but still is in the investigation.
Okay, do we have any last questions? Let's thank Link one more time. Okay, so our next speaker will be joining us remotely, Phil Bull from Queen Mary, University of London. This might take some doing to get set up. Phil, maybe you can give us a sound check?
Can you try to speak, Phil? Try again?
Okay, how about this?
No.
People hear? No.
Again?
How about now?
It's going to be complicated.
Okay, so
Maybe with
twice this one.
Yeah.
Okay, go ahead.
Okay, how about now?
Is it? Yeah? Can you hear it? Perfect. Okay, I think you can start anytime.
Okay, great. Thanks very much. And thanks very much to the organisers for accommodating this remote talk. So sorry I couldn't be with you. Please speak up if I go faint or start sounding like a robot more than usual or anything like that. Okay, so I've been asked to talk about cosmology with the square kilometre array and its precursors. So obviously these are all radio telescopes. So onto the first slide. What is the point of doing cosmology with radio telescopes in the first place? So one of the nice things about radio telescopes is they give you a lot of flexibility in how you're actually recording data from the sky. So some typical nice properties of them are things like you can construct a telescope with very high angular resolution, and there are very few atmospheric seeing effects typically. These things are inherently spectroscopic instruments, so you get spectra in every pixel or something equivalent to a pixel. Another nice property is you're directly measuring Fourier modes. If you're using these things as interferometers, you're pretty much directly measuring Fourier modes on the sky, which is unusual and interesting compared to typical optical telescopes. And as I mentioned, so they're pretty flexible. So they're essentially just big hunks of metal on the ground. It's easy to just walk up to them and bang them on the side with a wrench or something like that, which is quite nice if you need to tweak them. And you can also do things digitally as well. You can reweight the PSF and all sorts of other nice real-time modifications to your data stream as it comes in. So those are some positives about the instrumentation. In terms of the radio sources themselves, so the radio sky is quite different. Dust obscuration really isn't a problem, and in fact there's very little absorption of any kind. And this is really neat because for a very long time we've been able to see very high redshift sources in the radio because of this. You also have quite exotic source populations. I'm thinking about things like AGN with gigantic jets coming out of them, fast radio bursts, whatever they are, and so on, all of which have some promising features for maybe doing cosmology with them. You also have a ubiquitous class of emission line galaxies. Pretty much every galaxy has a ton of neutral hydrogen in it, and so you get a 21 centimeter emission line, and you can use that for spectroscopy. That's pretty much every galaxy. Another nice point in some ways is that radio galaxies, or galaxies seen in the radio, their SEDs tend to be quite a bit simpler than what you'd see in the optical or infrared. That's a double-edged sword, though, as we'll come to in a little bit. Okay, so if radio instrumentation has all these nice properties, and if the sources have all these nice properties, where are all the cosmological radio surveys? And the answer is really to do with the lack of scale. So current telescopes are just a bit too small. So to be able to really do a big cosmological survey of most kinds, you need high resolution, high sensitivity, and for this kind of radio telescope, that translates to lots of collecting area and many baselines, so many pairs of antenna with a wide range of different separations. So to get really good quality imaging from a radio interferometer, you need baselines, and lots of baselines, ranging from a few meters, a few tens of meters in length, to maybe about 100 kilometers in length. So these things have to be big. With the kind of size you need, that you get the curse of needing a just gigantic computer to be able to process all the data coming in. So for the amount of, or the typical amount of frequency channels, the amount of antennas we're thinking of for the next generation of telescopes, we're talking about data rates around 5 terabits per second, just the raw data rate going into the thing. And to process that properly, to do all the calibration, to reduce the data, the estimates are something like 250 petaflops peak for something like the first phase of the square kilometre array. So for context, the current #1 supercomputer in the world, Summit, has a peak floating point operation rate of about 200 petaflops. So when SK1 actually comes online, you know, the state of art will have evolved, but it's still going to need pretty hefty computing. And you can see that it's only now that something of this scale is becoming even remotely possible. So I think in large part the reason why we don't have many particularly big cosmological radio surveys at the moment is just because the computing hasn't been big enough, and so we haven't been able to build big enough and sensitive enough telescopes. So one takeaway from this talk is that this has changed. It's changing right now, and we're kind of on the cusp of having the raw computing power we need to actually drive these huge things. Okay, so onto the square kilometre array itself. What actually is the square kilometre array? So in a nutshell, it's a multi-site, multi-generational radio observatory. Okay, so by multi-site, I mean it's actually consisting of several radio arrays, low-frequency and mid-frequency arrays. They're separate. The low-frequency array will be in Australia, the mid-frequency array in South Africa. So they don't even need to be on the same continent, but we're still calling it the SKA. And it's going to be built in several phases. In fact, it is currently being built in several phases. And we'll go over that in just a second. I think a point that's important to make for cosmologists, though, is that the SKA is not intended to be specialized to surveys. It's designed to be a very capable survey instrument, but there are many other modes of science that you can use it for. So I think the fairest comparison is with something like ALMA. So there's going to be a mix of key science and PI projects. There's going to be people looking at individual objects, and there's people going to be doing surveys of 10,000 square degrees or more. And so all of that has to be kind of folded in. It's not a single shot survey instrument like many cosmological surveys that we're used to. Okay, so this is just to give you a kind of feel for what I mean by this multi-generational aspect. So along the x-axis, we've got instantaneous field of view. This is a good statistic to use to figure out how fast a telescope will be at surveying. And on the y-axis, we've got point source sensitivity, which is a decent proxy for its raw sensitivity. And you can kind of see a lot of current telescopes are marked on there. They mostly fill this kind of band that's marked out by the blue and green lines. But then above those, you have what I'd really say was the 0th generation of SKA, which is the precursor telescopes. Meerkat and ASCAP are included here. The next generation is the separate SK1 arrays that I just mentioned. The mid-frequency and low-frequency ones will be there. And then much more futuristic is phase 2 of the SKA, sometimes called the full SKA, which is a little bit of a nebulous concept at the minute. So I'll mention more about that later. But the ones to really focus on are the green and the blue circles, ellipses here. Okay. So as I mentioned, the kind of 0th generation of these precursor telescopes, probably the most important ones for large-scale structure cosmology are Meerkat and ASCAP. So Meerkat is a 64-dish array with single pixel feeds. That's in the Karoo Desert in South Africa. And ASCAP, which is a slightly more novel thing. It's only 36 dishes, but each dish has a 36-pixel receiver. So both of them are pretty capable survey telescopes. They are bigger than any existing dish arrays like the VLA that we're currently used to. And they're operating right now. They've been fully constructed. They are pretty much done with their commissioning, and they're actually starting to operate and starting to do initial surveys and initial observations. And so to kind of prove this to you, I've got some pretty pictures. So here is an initial commissioning survey from Meerkat of just a small strip of the galactic center. And it's actually folding in some additional data from GBT as well. But most of this is Meerkat. And if you're used to looking at radio images, you will be pretty startled by the level of detail, and especially the level of detail on many different scales. So we're not just seeing the fine detail, we're also seeing some large-scale detail as well. And obviously there's some very complicated stuff going on in the center of the galaxy. I don't know much about that, but I do like galaxies, so I'll circle a few radio galaxies for you. I don't know if you can really see that in the room, but you should be able to see about 3. I'm pretty sure these are radio galaxies with huge jets at quite some distance. So these are obviously behind the galactic center. So this is a image with huge dynamic range, both in terms of the scales, the angular scales that you can see, and also the brightness of the various things you can see. So this is really nice. Meerkat's performing well, it seems. I want to show you something from ASCAP as well. So ASCAP has done an initial mini survey of the small Magellanic Cloud, and what you're seeing here is essentially the density of neutral hydrogen, H1, in the SMC. They picked a very cool color scheme that makes it look like everything is on fire, so that's pretty good. But the main point is, you can see that these telescopes are up and running, and they're producing absolutely beautiful images, stuff that we're really not used to in the radio. So this is something new. Okay, so onto SK1 itself. So SK1 mid is the array that I want to concentrate on today, because that's the more relevant one for large-scale structure cosmology. And so remember that Meerkat was about 64 dishes. SK1 mid is about 200. 15-meter dishes, they're in quite a balanced layout. So you have a few dishes that are very close together, like in the image. And then you have a number of dishes that are spread over quite large distances. So this is nice because it gives you quite a balanced baseline distribution for doing imaging. And there are 2 main bands that we're mostly interested in for cosmology, band 1 and band 2. And they essentially cover, redshifts from about 0 to 3, if you're looking at the 21 centimeter line. Okay, so an important thing to appreciate about SK1 is that everyone is a bit confused about the schedule. The schedule keeps evolving like any complicated project. And so at the moment, as far as we can tell, we're on track to do some commissioning surveys around 2025 to 2026 and start some big key science projects from 2028. Obviously, nothing's set in stone though, but you know, this is the information we have at the moment. So it seems a little bit futuristic, but remember that SK1 mid is made up partially from Meerkat, and so we already have something like, I don't know, roughly a third of SK1 on the ground and up and running right now. So it's not like we have to sit here and wait. Okay. Just to give you some idea of the kind of leap in capability once you add this many dishes, here's a comparison, a simulated comparison of an SK1 mid snapshot. So that's just taking data from all of the baselines, but for a short amount of time, and constructing an image. That's on the left. And on the right, you've got the equivalent for multiple VLA snapshots using 4 different VLA configurations. So they can move the dishes of VLA and get different baseline lengths, and you can just see the difference. It's quite remarkable. So obviously you're seeing many more Fourier modes, and with a nice bump in sensitivity too. And SK1 mid also has wider bandwidth and generally a greater field of view, which gives you a higher survey speed. Okay. So on to the cosmology that this enables. So this is just a kind of schematic of the kinds of surveys we can do, and I've roughly characterized them by their redshift resolution and their angular resolution. So the most conventional type of survey is in the top right. It's just a regular spectroscopic galaxy survey. So you detect galaxies, you measure their spectra. Now you've got pretty good 3D localization of each galaxy in your survey. Okay, and we can do that with a 21 centimeter line from neutral hydrogen. In the bottom right, there's something that's a bit like a photometric galaxy survey, instead using the continuum emission from radio galaxies. That's mostly coming from synchrotron, but the spectra are more featureless, and so you can't really do photoz's with this kind of galaxy, at least not very accurately. So these are more or less two-dimensional surveys. You have a very good idea of where the galaxies are in angle, but in terms of their redshift, you don't have access to much information that will help you figure that out. Okay, and then in my view, the most exciting is in the top left, which is H1 intensity mapping. So again, using the 21 centimeter line, but instead of shooting for angular resolution, you accept lower angular resolution and kind of average over many galaxies per pixel, and so that helps you build up a more sensitive map of all of the emission, and you can recover the large-scale structure without necessarily resolving any individual galaxies. But this is all with spectroscopic redshift resolution, so this is still a 3D survey. It's just you don't see individual galaxies. So all three of these types of survey are modes of operation that the SK and its precursors can use, and you can actually use them all at once. So from the same data cube, you can in principle extract all three types of information. Due to systematics, it's a bit fiddly to do all three at once, but we're pretty sure you can do all three. Okay, so just to give you a kind of overview of the relative capabilities of these three generations of SK survey. So we've got Meerkat, SK1 mid, and SK2. I've got estimated timeframes and a rough idea of the number of dishes or sensitivity elements that we'd have. So SK2 is, again, this nebulous thing, but it's supposed to be about 10 times more sensitive. Of those, it's planning a very deep one out to high redshift and a relatively wide one out to redshift 0.4, where relatively wide in the current state of the art means 20 square degrees. Okay, so that's not useful to get 0.4. So we're talking typically 5-6 million galaxies for our current predictions, broadly similar to BOSS. For the continuum galaxy imaging, the numbers are much higher. It's much easier to detect galaxies if you don't have to also detect an emission line. So for something like Meerkat, we expect something like 10 to the 7 continuum galaxy detections, but not with particularly high resolution. So I'm not sure you can measure the shapes of many of these things very well, for example. That will all change with SK1 mid, though. We'll see an order of magnitude more galaxies out to quite high redshifts, and we should be able to resolve them quite well. And then SK2 will blow that out of the water. And then for H1 intensity mapping, I think this is where the real story is at the moment for cosmology. With SK, so even with Meerkat, we should be able to do a pretty respectable 4,000 square degree survey, covering redshift 0.6 to 1.4, which should be quite useful for BAO. And then for SK1 mid, should be able to, in principle, cover redshift 0 to 3 over about half the sky. And that will be quite competitive. SK2, we probably don't need to do intensity mapping because it's going to resolve most of the H1 galaxies anyway. But again, that's quite futuristic. Okay. So just to highlight, Meerkat can do useful cosmological surveys right now. It can, in principle, do these big continuum and H1 intensity mapping surveys. And in fact, these are planned. So these are planned for the next few years. So we should start to be getting some decent radio cosmology data sets very soon. Okay. So just to give you a bit more of a detailed flavor for what these particular surveys can do in terms of their science capabilities. So for the Spectroscopic Redshift Survey for SK1, we're talking about something that's comparable to BOSS, but about 10 years later. So it's not super exciting in that respect. The galaxies have quite a steep selection function for SK1 sensitivities, so we're mostly restricted to quite low redshifts. But we should be sample variance limited out to about redshift 0.4 for a 5,000 square degree survey. And we should get a particularly high number density of these sources at very low redshifts. We should be massively oversampled at low redshifts, which is interesting if you're thinking of doing multi-tracer type analyses, for example. Again, because it's so similar to BOSS in terms of volume, the forecast for the BAO and RSDs are quite similar. But there is a neat thing we can do because of the high spectral resolution. We can do a large and homogeneous Tully-Fisher velocity survey. So in principle, we can directly measure velocities in a nice and controlled way. So that would be quite an interesting data set, I think. For the continuum survey, there are a few things you can do with that. I'll focus on weak lensing though. We expect something like 20 galaxies per arc minute squared, which would be quite complementary to especially DES. We don't have much redshift information because it is continuum, but we should be getting cosmological constraints similar to DES. Again, remember this is a number of years later than DES, but it has some nice features in terms of how we can combine the radio weak lensing data with the optical weak lensing data to try and study systematics. So for example, you have a lot of flexibility in how you define your PSF in radio surveys, and you can even measure shears directly in Fourier space, which is, again, another interesting way of trying to make sure you've actually measured the real shear field and not some systematics. Okay, so I know we'll have a talk on intensity mapping next as well, so I'm not going to dwell on this for too much, but like I said, I think this is the kind of sharp end of SK cosmology. So the important thing here is that we should be able to access quite high redshift and very large volumes of the universe by doing an intensity mapping survey with these large radio telescopes. And the reason for that are reasons I've already mentioned. So H1 is ubiquitous, and you know, most galaxies have H1, and we can build these nice radio telescopes with huge bandwidths. Okay, with the SK, it does mean we get some resolution effects. So we mostly want to use it for sensitivity reasons. We mostly want to use SK as a bunch of single dishes when we do intensity mapping. If we use it as an interferometer, it's a little bit too loosely packed, and we don't get the sensitivity we need. But if we use it as a collection of single dishes, it's actually very sensitive. The problem is, if you only have single dishes, your resolution degrades like lambda over d, and so at higher redshifts you end up not resolving the transverse BAO very well. But there are these papers by, for example, Paco Villascusa Navarro and others, where they've shown that the radial BAO can be recovered very nicely at redshifts greater than 1, even using this mode. And with an appropriate weighting scheme, I think you can even recover a decent amount of the transverse information too. So just to give you some actual numbers, here are some forecasts for combined BAO and RSD. and a comparison with a Euclid-like galaxy survey and a HETDEX-like galaxy survey in black and gray. The Euclid one is probably a little bit optimistic, but these are Fisher forecasts. They're always optimistic anyway. And what you can see is that at the lower redshifts, intensity mapping outperforms the H1 galaxy survey, as you kind of expect. And at higher redshifts, the SK intensity mapping survey is broadly comparable with something you get from Euclid in terms of these constraints. And the reason the pink line has this evolution with redshift is due to these resolution effects I just mentioned. Okay, so I think I'm coming to the end of my time, so I'll wrap things up. I just want to briefly mention a kind of unique thing that you can do with this type of survey that's a bit more difficult in the optical or near infrared is you can really go to very large volumes and try and recover information on ultra-large scales. So this is well known as a place where looking for scale-dependent bias from non-Gaussianity is quite fruitful without having to go to the bispectrum. But there are also some relativistic effects on such large scales as well, which would be very nice to measure as a test of general relativity. Now, the signals are very small and your cosmic variance limited, so you either need to really increase your volume to the max, or you want to cross-correlate multiple tracers. And again, that's something we've been studying with SK combined with LSST. And it looks like you should be able to get sigma FNL of a little bit less than 1 if you know, you're reasonably optimistic about your foreground assumptions and things like that. Okay, so I'll summarize. So the first truly large radio galaxy surveys are imminent. We're expecting something like 100 million galaxies at redshifts out to about 5 with SK1 continuum observations. But only about 5 million spectra for SK1. With SK2, that's supposed to be 10 times more sensitive, we're talking about 1 billion spectra, which is huge. But the point is, even if this looks futuristic, Meerkat and ASCAP are already on Sky and Cosmology capable. And we expect to get some pretty decent surveys out of them in the next couple of years. And then the other points are just things I've already gone over. SK1 isn't particularly competitive with optical and near-infrared surveys in terms of figure of merit, but there are some nice things like Tully-Fisher surveys we can do, which are reasonably unique. And intensity mapping is the more competitive of the survey types, and should be pretty useful. So I'm going to stop there. Thanks very much for your attention, and I can't hear anyone, so yeah, speak up.
Okay, thank you very much. Phil, can you hear us?
Yep, I can hear you, but you're a bit feedbacky.
Yes.
Okay, the feedback stopped. It was cool though.
Okay, we have time for maybe one question.
I think we need the microphone there for Phil.
Can someone repeat that?
I didn't, I'm sorry.
Foregrounds. You didn't say a word about it.
Foregrounds, they're fascinating.
Can you hear me?
Okay, so our next speaker is Isabella Carucci from CEA.
Thank you. Yeah. Can I see? Okay, good morning, everybody. So I will follow Phil's talk and keep talking about 21 centimeter in intensity mapping. So I don't have to introduce it too much, thanks to Phil's talk. So I'm talking about detecting the 21 centimeter radiation emitted by neutral hydrogen in the universe, and doing so without resolving each single source that is emitting. So basically scanning the sky, looking for the radiation with even bad angular resolution. But at the end, what we will get are maps at different frequencies with temperature in 21 centimeter. Slightly like the CMB, to give you an idea. But we will have a 3D information because we will have many of these maps. It depends on the frequency resolution of the instrument we are talking about, but I mean, of the order of, like the Redshift slice will be of the order of 0.01. And you will have 3D information, and we can do nice things with it. So is it even possible? Somebody was mentioning foregrounds in the question. The answer is yes, and it's simply because somebody already did it. The first measurement was in 2010, Suchi Chang, with the Green Bank telescope, thanks to cross-correlation with Z galaxies. But later on in 2013, they came with an auto-power spectrum measurement. You already can see from this plot, like here is what they measure, and these are the reconstructive foregrounds, so the difference is huge. And more recently, also in Australia with the Parkes telescope, they got a cross-correlation in intensity mapping with galaxies. So if you're not convinced, so many other people are already. This is a list, I don't know if it's complete, of instruments that are going to do 21 centimeter intensity mapping. In bold are the instruments that I know are doing something with data. So it's something that is happening right now. The first one is Meerkat, and Phil extensively talked about it. And it is doing also, like it's testing also a 21 centimeter intensity mapping survey-like. Some of these instruments have been built specifically for doing intensity mapping. So this is the outline of my talk. I will say a bit about what's the stage and modeling of the signal, because we need it in order to understand what is the dependence of cosmology of the signal. And then I will touch a little bit the foregrounds, and if I have time, say something also about synergies with other probes. So let's start with the modeling. So what do we know about the large-scale structure distribution of neutral hydrogen in the universe? Not much. It's really hard to detect galaxies without the SK in the H1 line. So we do have surveys, but really in the local universe, Redshift 0. And we have this bias. The first value here is the bias of H1 selected galaxies. But we know something about damped Lyman alpha systems, which are the biggest absorption systems that you have in the spectra of faraway quasars. And we believe these objects contain most of the neutral hydrogen of the universe at this redshift, and this is the bias. So you can already see, like it looks like there is a big change in bias over redshift evolution. And then from the Switzer et al. Auto-power spectrum, they derived also this number for the combination of the abundance of neutral hydrogen in the universe and the bias. By the way, a 21 centimeter intensity mapping survey alone will be able to measure just the combination of these two, because the overall amplitude of the signal is proportional to them, so they generate. So what do we do with these numbers? Without even entering the discussion of the bias, even just tackling the problem of how much hydrogen is out there, because your signal will be proportional to it. It's not an easy, I mean, we do have numbers. So this is the omega H1 as function of redshift. So these are data points coming from Lyman alpha forest, for example. But the errors are large. There is maybe a redshift evolution of this quantity, but it's unclear. So what do we do? Well, there are things that we know. about neutral stuff in the universe. We know it's not in filaments after ionization. And we know because we measure the forest of in the quasar spectra, and all these lines are intervening small neutral hydrogen clouds that have been unionized by the quasar light. So we can measure how much neutral stuff is left there, and it's really few, not enough to produce a 21 centimeter line. So the guess is that it must be in galaxies, in halos, in the densest environment that we have. So as a first approximation, I can say, well, just place the neutral hydrogen in dark matter halo. So if I have dark matter simulations with my halo catalog, if I know the relation between the mass in H1 and the mass of the halos that is hosting H1, I can populate my simulation and understand, make a mock of the signal. Do we know this relation? So, well, kind of. There are many tentatives of understanding how this relation looks like. Some of these people, so this is mass in neutral hydrogen as function of mass of the halo that is hosting it. And some of these people have calibrated this function with hydrodynamical simulations. Others have chosen to fit the bias of the DLAs, and you get different answers. The second strategy is, well, we have hydrodynamical simulation, let's run them. Of course, the different hydrodynamical codes give different answers. I don't want to get in this discussion. And moreover, you need cosmological volumes. So the hydrodynamical simulation is not enough because it doesn't run a full radiated transverse code inside the galaxy. So you need also some post-processing. So you add a recipe on top of your dynamical simulation. So you can do it, but of course the answers are really different, especially if you look at redshift higher than 0. Like everything is converging at redshift 0 because this is how hydrodynamical simulation are calibrated. But then when you look at redshift higher than 0, they're different. But we have a way to test this different modeling of where to place the neutral gas, and this is because we measure the Lyman alpha, the Lyman alpha forest, and so we have measurement about the H1 column density distribution function. So the number of this absorption system as function of the column density neutral hydrogen. So for example, here, it's not important now, but these are two different ways of modeling the H1. And then you see some of them are doing better at this end of the plot, and some others are not. So there is a way to test them. And so we are at this stage in which we think we know how to model the signal. We can do it also with chip and body, tuning our H1 halo mass relation. And we are able, adding noise and beam effect and so on, to prepare forecast. So now that we know how to model the signal, we can ask, OK, so what's the dependence on cosmology? What kind of cosmology we can do with it? So cosmological model, we measure the parameter with great accuracy, but what is dark matter and what is lambda? So fundamental question, let's start with dark matter. So under the large-scale structure point of view, the success of dark matter is in this picture. No? You have the matter power spectrum as function of scale, and you have all the different probes from CMB to galaxy clusters, weak lensing, and down to the Lyman alpha forest that are probing this power spectrum at different scales, and everything is consistent. So all models of dark matter that are around overlap with this picture, of course. Where the models start to behave differently is at the very end of the small scale of this plot. And this is because, sterile neutrinos, fuzzy dark matter, whatever is your favorite model, they all have some sort of dissipative effect that does produce a suppression in power at the small scales. And this is not just a particle physics thing, but it's also pushed by the observation that we do at below megaparsec scales. And I won't enter in the details, but there are problems at the galactic scale that seem to be alleviated, at least, if you do have a cutoff in the matter power spectrum at small scales. So why I'm telling this to you now, so what is the 21 centimeter intensity mapping going to add to this picture? We're not going to probe very small scale with it, as I already said. So, but the answer is that we don't need to go to probe really small scale with the 21 centimeter because every time you have a cosmology in which you have a suppression of power small scale, the whole signal is boosted at those scales up, just because the matter power spectrum you started with as a cutoff. So this is really good news. But why is this the case and how did we get to this answer? So we ran simulations, both n-body and aerodynamical. Here I'm showing a perfectly cold dark matter one, together with the 1 kV thermal relic mass. I don't know if you can see by high what's the effect of these models. Everything is smoother, you have less substructure. Being quantitatively, this means that in the matter power spectrum, between perfectly cold and other models, you have a cutoff that can be 20% or less according to the different model you're looking at. The same thing if you look the halos, so this is number of halos as function of their mass, all the halo mass function, and here is the residuals, and then you see that these models predict small halos in less smaller number. Okay, and this is it, the result. So after I apply all the modeling of how to place neutral hydrogen around, this is what we get. So this is the difference in power in signal between each of these models I'm looking at compared to a perfectly cold and in percentage. So you can have difference of 3% up to 100% higher in the signal. And so different color, different lines are different models, and the shaded area is the SKA low instrumental noise that you expect. So there is room for an instrument like SKA to tell these models apart in great accuracy. Why is this happening? We think it's because in the moment in which you have a cosmology with less substructure, it means that this neutral hydrogen has to be placed in the smaller halos left that are bigger and also have a bigger bias. So it's more cluster and your signal goes up. This is happening also, as I said, for all these models that have a power spectrum cutoff. I'm showing this plot because it's with the ultralight axions. We discussed about them 3 days ago with Daniel's talk. And here you see the same effect. This is the same kind of plot, the difference in power spectrum of the signal between this ultralight axion model compared to cold dark matter. And you see the difference is huge. And here there is even lower because I'm looking at lower redshift, so I'm using SKA mid. This is true for whatever model that modifies a little bit your growth history. We tried, for example, with the dynamical dark energy. And again, here, I have the same kind of plot. For example, for this Ratra-Peebles potential dynamical dark energy, there is room for an instrument like SKA mid in order to tell these models apart. So a little bit about foregrounds is the ugly beast of this business. So I was a little bit cheating, showing all these nice plots with these really small errors. These are just the thermal noise of the instrument. The truth is that foregrounds are a big challenge for 21 centimeter intensity mapping. And it's because they are huge compared to the signal. So this is in intensity, the different components as function of latitude, so close to the galactic plane going up. And then you see that, for example, the biggest, highest component is the galactic synchrotron, and is 4 orders of magnitude higher than your signal. That is the black line here. It's a noise line thing. And then you have, of course, free, point sources, radio background, and it's really challenging. So far, people have tackled this problem by using techniques that take advantage of the fact that most of these foregrounds have a well-behaved frequency behavior in that they're smooth. They're smooth in frequency, whereas your signal is noisy. The problem is that you have things like polarization leakage, this red thing. It's just due to the instrument itself. And that is really hard to model, and moreover, we know it has a non-trivial frequency dependence. Look at this one here. So these techniques are going to fail in order to extract also things like the polarization leakage out of this data. What we are trying now at Cosmostat is using GMCA, Generalized Morphological Component Analysis, developed by Jérôme Bobin. And this technique is not based on the smoothening frequency of your foregrounds. it's based on sparsity. So basically, at the same time as the usual data fidelity term in order to retrieve your components, you also enforce sparsity in a wavelet base of your components. And this is because 21 centimeter signal is going to be everywhere, but all these ugly, nasty foregrounds are at the galactic level. So at the level of the pixels, you can play this game without relying on, without tuning anything or without relying on the smoothness of the foregrounds. So we're testing it now. It's really preliminary. But I think it's the first time that somebody is included polarization leakage in the simulations. And we are, like the code, even at this preliminary stage, is already behaving well in the sense that it is able to extract also this sort of foregrounds. And my time is up, so I won't say anything about synergies, but I leave you with my summary, and thank you for listening.
Okay, well, thank you for finishing on time. We have time for questions, so any questions?
Yeah, how are you modeling your polarization leakage? How are you modeling your polarization leakage in a simulation?
Sorry, say it again.
How are you including polarization leakage in simulation?
Okay, I'm following this Alonso 2014 that I'm citing here. Basically, you start with the polarization of the synchrotron. And then you need to add on top of that the magnetic field of your galaxy, and then somehow mimic the Faraday rotation of the photons coming to you. And it's complicated. And
maybe you can use a polarization map, simulated polarization map by...
Like Hammurabi?
Huh?
The Hammurabi code?
Not Hammurabi. Yeah, Hammurabi is one, but actually it's simulated from data by Faraday rotation measurements. I'm forgetting. Maybe we can talk later about that.
Thanks.
Further questions?
On your interesting results about in warm dark matter scenario, you see an increase of the amplitude of the power spectrum, and like I wonder how you paint the H1 or stuff onto the warm dark matter simulation. Do you assume any universal H1 fraction versus dark matter fraction?
So we do both, and the answer is the same. Of course, like for example, in this plot, each color is a dark matter model, but then the solid and the dotted line is two different models. One, I tune it, and the other one, I just run the dynamical simulation. So actually, I don't do anything. There is difference, but the point is that both of them make the amplitude go higher.
Okay, any further questions? Great, well, let's thank Isabella again.
Thank you.
And our next speaker will be Mona Jaliland.
Yes.
From Geneva.
Geneva, yes.
Okay, welcome.
Thanks. Can you hear me? Yes. Thanks. So I'm going, first I want to thank the organizers for giving me the opportunity to talk here. It's a great pleasure. I wanted to talk about a new estimator for weak lensing based on cross-correlation of 21 centimeter intensity mapping and galaxy clustering. I'm a PhD student from University of Geneva, and we've done this work with our collaborators from University of Geneva and University of KwaZulu-Natal. So I put the topic from Planck to SKA to Euclid, which So the future 21 centimeter surveys will probe high redshifts. We have observed the universe at redshift 1100 from the CMB radiation and up to redshift of order 1 from galaxy surveys. And 21 centimeters will allow us to probe the intermediate redshift ranges and allow us to test our models in a wider range of distances. So we need to build estimators and observables to use this data to test our models. Weak lensing is one of these estimators that probes matter distribution, and it is a test of our gravitational models. So I will give an introduction to weak lensing of galaxies. What is the effect of lensing on observed galaxies? One effect is shape correlation through the effect called cosmic shear. So if you look at this intersection of the diagram, you see unlensed distribution of galaxies. And here you see the lens distribution of galaxies by the cluster on the way. So you see that the shape of the galaxies is somehow aligned around the lens. And this is due to the fact that all of them are lensed by the same structure. And Marika explained very well in her talk. This needs precise shape measurement, and Henrik and Marika talked about the systematics that should be taken care of. But another effect that doesn't need precise shape measurement is that lensing changes the number density fluctuations of galaxies. If I look in the sky at a redshift slice and count galaxies in different directions, I see perturbations. Wherever there are more dark matter, I see more galaxies, and they are related to a factor bias. But of course, lensing can change this galaxy number count. So what lensing does is to change the transverse distance between the galaxies. So if the red lines are the geodesics in the background, and the blue line is the light ray that is lensed by a structure, by the matter on the way. It expands the transversal volume, so therefore it dilutes the number of the galaxies that we see. This effect is taken care by this term, 2 times Laplacian of phi, where phi is the lensing potential and is an integral over the Weyl potential all the way from the redshift of observation to the observer. And as Alessandra explained in her talk, the relation between the Weyl potential and the matter distribution depends on our gravitational model and can be changed via mu and sigma parameters. So therefore, if we detect lensing, we can test our models. But there is another effect due to lensing. Lensing magnifies, it increases the luminosities of galaxies. So we see the galaxies that we couldn't see them without lensing. They were below the threshold of our telescope. So this effect is governed by this sentence. S is the magnification bias parameter. So at the end, the competition between these two terms changes our galaxy number count, and it's called magnification bias. Now I give an introduction to weak lensing of 21 centimeter intensity mapping. It's exactly like CMB. We have heard a lot during this conference. In intensity mapping technique, we don't aim to detect individual galaxies, but like CMB, we look at large pixels in the sky. We measure the intensity in each pixel, intensity of 21 centimeter radiation. And again, we see fluctuations in this intensity that is related to dark matter density fluctuations by a bias factor. But there is no first order lensing despite galaxies, because due to Liouville theorem, the lensing observes surface brightness. And if the volume is expanded, more photons will enter, and at the end they compensate, and we see no dilution in the number of photons. But of course, lensing has second order effects. So the hot spots and cold spots will be displaced because of lensing, because the light ray that travels from them to the observer will be deflected. And it is a second order effect. If you look at the Taylor expansion of this deflection, you see that we have delta times the gradient of phi, which is a second ordering perturbation. In another work with Ruth and Martin and Beta, we studied this effect. I just want to give two quick messages from the other paper, not to deviate from the main story, that we found that post-Born approximation is important for second-order lensing of intensity mapping, and second-order lensing can bias our parameter estimations and should be taken into account. But now I come back to this feature that intensity mapping has no first-order lensing. So let's first look at the standard estimator that people use for detecting magnification bias. So the galaxy number count is unobservable, but it's not predictable. I cannot tell you if you look at this direction in the sky, it's an overdensity or underdensity, it's a random field. But the statistical property of this field is predictable by our models. So people usually look at the cross-correlation of galaxy number counts at two different redshifts. At a background redshift, they cross-correlated with the foreground redshift. And what we get in the power spectrum is a density cross-correlation. So the correlation between the density at a background redshift and the density at a foreground redshift. We get a lensing density correlation. This term is due to the fact that the lensing at the background redshift is an integral over matter distribution all the way to the observer. So of course it is correlated with the density at the foreground redshift. And we have a density lensing correlation which is very small because the lensing at the lower redshift is not correlated with the density at the higher redshift. And finally, we have the lensing correlation, the lensing of the background redshift and the foreground redshift, and it's due to the fact that both galaxy number counts are affected by the matter on the way. Now I want to give the introduction to our new estimator. So we use this feature of intensity mapping that doesn't have first order lensing. And we thought of this estimator to, so if you correlate galaxy number count at a higher redshift with intensity mapping at a lower redshift, you will get, so galaxies are lensed by the intensity, by the matter on the way, so we will have a density correlation term and a lensing term. But if we correlate intensity mapping at a higher redshift with galaxies on the way, intensity mapping is not lensed up to first order. So up to first order, we only have density correlation. Now, if we subtract these two correlation functions, we can get rid of the density term. So we will end up with an estimator that is cleaner for detecting lensing. So let's look at our estimator. So here I have cross-correlation of galaxy intensity mapping minus intensity mapping galaxy. As you see, the density term is proportional to the bias difference. So if we want to detect lensing and test our gravitational model, density term is contamination for us. Here, the contamination is reduced by this bias difference with respect to the standard estimator that people use. So let's look at an example of the contamination for a redshift pair of 1.21 and 1. So here I'm plotting the ratio of the contamination term, the density term, to the estimator. The blue line is the standard estimator that people use, and the orange line is our estimator. As you see, the contamination for this pair is 40% for the standard estimator, and it's only 1% for our estimator. So if you want to use this redshift, thanks. If you want to use this redshift pair, our estimator is much better, and you can safely use it. But this is not the only difference. People can say that, okay, we look at very large redshift separations in galaxy-galaxy clustering, and we get rid of the density term, so we go to higher redshift separation than this. But our estimator has another advantage. So we can get rid of density term in cross-correlation, but we can't get rid of it in variance. In variance, the autocorrelation term appears. So this is the variance of the standard estimator. We have the autocorrelation terms and a cross-correlation term. And this is the variance of the our estimator. as you see, if we group these terms together, again, we end up with the autocorrelation terms that are reduced by a factor that depends on the bias differences. So our estimator also reduces the variance. Here, I'm showing the signal to noise for a specific pair 1.3 and 0.8. So the top plot is for the case of cosmic variance limited, no noise. The orange line is our estimator, and the blue line is the standard estimator. So in this case, in cosmic variance limited, if we use the information up to L max of 200, our estimator improves the signal to noise by a factor of 20. But if we add noise, of course, the signal to noise goes down, and our estimator improves by a factor of 6. So here I'm showing 3 plots. I just mentioned what they are. So the blue line is the standard estimator. In the literature, there are 2 formulas for thermal noise that are widely used, and they have 4 orders of magnitude difference. So the optimistic, they assume an optimistic assumption, and it is good apparently for SKA low, not near future surveys, but people use it. So we did our analysis with 3 different cases of noise. And the pessimistic noise, we took it from Radio Fisher code written by Phil Ball. This is closer to the reality. But we have some indication from the HIRAX team that they have done simulation for HIRAX and with more details, that the noise that they get is 1/10 of the noise that we get from Ball code. So in fact, the green line is, we call it realistic case because it's it's the result of simulation, so we trust it better. In the realistic case, we get a factor of 6 improvement with respect to the standard estimator. So this was just one pair. So if we do the Fisher forecast for lensing amplitude using all the pair possible to see how well we can detect lensing, so we use the redshift differences more than 0.3 to get rid of the contamination. And this is the result of the final signal to noise using all the redshift pairs possible. The top plot shows the signal to noise ratio for DES HIRAX. In the realistic case, which is the red line, compared to the standard estimator, we get a factor of 1.5 improvement. And for Euclid HIRAX, in the realistic case, we get a factor of 2 improvement at redshift. Okay, the improvement depends on the redshift, but at redshift 1.5, we get a factor of 2 improvement. And if you want, if you want to test your model in these intermediate redshifts, our estimator is much better. So this brings me to conclusion. Our estimator reduces systematics because it's a cross-correlation between data from 2 different surveys, and it reduces contamination and allows us to use closer redshift bins in our Fisher forecasts, and it increases signal to noise by a factor of around 2 for free. I mean, the data is there without spending millions of dollars. We get this improvement for free. Thanks.
Okay, questions from Anna?
You didn't mention redshift space distortions, but presumably those are present in both of these fields. So does that also contaminate this estimator?
Right. So I forgot to mention that we use wide redshift bins with widths of 0.1, so that redshift space distortion is not important for our bins.
Also, perhaps relevant to that, in this case where you use essentially 2 tracers to increase the signal to noise, do you also have to guarantee that these 2 tracers exactly in the same redshift range?
Yes, in fact, for I would say the very interesting point about our estimator is that for dense hierarchs, we only use the redshift range of 0.8 to 1.3, while for dense, we are using the redshift range of 0.2 to 1.3, and still we get this improvement. So it's really, I shouldn't say, but it's really amazing. I mean, it's interesting.
Okay, one last question.
Do you know why your estimator is doing worse at higher redshift compared to the standard?
Yes, so the problem is that when we go to higher redshifts, we have less number of galaxies, and we have tested that our estimator is killed by shot noise more than the standard estimator. So at the end, the other estimator catches up, but still in a wide range, our estimator is doing better. Yeah, thanks.
Okay, let's thank Mona one last time.
Well, while this being set up, let me just get started so I can save some time. I'm Azadeh Moradinejad, and I'm currently a postdoc at University of Geneva and an associate scholar at Harvard. So first, I would like to thank the organizers for this wonderful workshop, and also for the opportunity to talk and tell you about some of our recent works with two of the other collaborators at Harvard, two other postdocs, on prospects of using intensity mapping, but not with the usual 21 centimeter line, but with other emission lines, and in particular with carbon monoxide, sorry, rotational line, and with a C2, fine transition line. So, as I said, this is the work that is primarily done in collaboration with Karto Keating, who is a radio observer at CFA Harvard, and in the initial stage with Anastasia Fialkov, who is a theorist. And Anastasia is now at Sussex as a faculty member, and Karto as a SMA staff at the moment. So we had a wonderful review talk by Michele about the importance of constraining non-Gaussianity and the prospects of future LSS surveys, as well as the current constraints from Planck. And also we heard an overview talk by Phil on intensity mapping as a general probe with a focus on 21 centimeters. So let me not go through a lot of the details of the introductory setup, but just to say that our current best limits on primordial non-Gaussianity, in particular on local shape, come from Planck. But the hope is that the future LSS surveys can significantly improve these constraints with a simple mode counting argument that we have a 3D map versus 2D map. So there are more modes, and in particular, there is more, in principle, there is more information. And then we can ask what are the LSS observables. Well, we can look at the abundance of rare events, like peaks, massive halos, voids, or we can look at the clustering statistics, and in particular, let's say on power spectrum or bispectrum. So for the purpose of this talk, I will just focus on using power spectrum of line intensity to constrain local non-Gaussianity in particular. So, so of course, we are very used to thinking of measurements of power spectrum from galaxy surveys, which resolve individual sources, and to measure the scale-dependent bias on very large scales to constrain local non-Gaussianity. But one can think of using line intensity mapping, which doesn't resolve individual galaxies, but instead look at the cumulative light from ensemble of sources. And of course, the advantage of these probes, in particular for local non-Gaussianity, is that it allows us to probe ultra-large scales. So now you can have different line candidates to perform intensity mapping. 21 centimeter, we heard a few different talks about using 21 centimeter for various cosmological constraints, but I'm going to talk about using CO and C2 emission lines. And of course, there is a wide range of science targets to use these lines. In particular, they have been often thought of probes of reionization and the questions such as bubble size, ionization state, metal production, and as a probe of star formation and galaxy formation, since they trace the cold gas, which is the fuel of star-forming galaxies. As a result, they can be a very strong probe for star formation. Now here, of course, I will focus on using them on large scales to probe large-scale structure. And the lines we are talking about have rest frames of 115 gigahertz for CO and 1900 gigahertz for C2 in comparison with 21 centimeter line, which is in the megahertz region. So of course, our forecasts are not the first one of using intensity mapping to constrain non-Gaussianity. A large body of work has been performed to study 21 centimeter intensity maps for this purpose. And here I'm just quoting two of the initial papers that performed the forecast, but of course there are a lot of updated forecasts accounting for various things. So the first one is from the high redshift 21 centimeter, whereas the lowest one, the second line is from the low redshift. Now, for the CO and C2 detection, you can ask, first of all, how we detect CO or C2 in high redshift galaxies? And the answer is there are detections from individual sources, individual galaxies, and quasars. And the most recent one are from Pavesi and Rikers. Pavesi is on ALMA measurements, while Rikers is from the cold Z sample of VLA. And there has been a first detection of the auto and cross power spectrum of the intensity map, one performed by Carto, my collaborators, or is it Keating et al., which is a measurement of power spectrum of intensity map of CO. And there has been a measurement of C2 power spectrum, but, well, not a power spectrum, but measurement of C2 via the cross-correlation with CMB. So having said that, let me just tell you what are the things we were interested to understand. So first thing first, we were interested on the question of how well these surveys can constrain FNL local and how competitive it is with upcoming galaxy surveys. So the first thing was a forecast for particular instrument setup, and we used some current designs for the instruments and the question of how well multitracer can help with that. And the second part of the study is a more detailed study. I'm not sure how much time I will have to go through that, but basically, since there is no currently designed survey for intensity maps with CO and C2, which targets a probe of FNL as its science target, we asked our question of what is the optimal survey design and instrument design to constrain non-Gaussianity in terms of sky coverage, redshift coverage, and instrumental noise. And of course, then the constraints you might get from the emission lines heavily depends on the astrophysics you assume. So we asked the question of how does it depend on various ingredients that went into modeling. And then as we heard, of course, foregrounds are a big issue for intensity mapping. So we kind of effectively account for foregrounds without really modeling the foregrounds for a given instrument. And then we also ask whether we can do multitracer with multiple lines. So Just to tell you quickly about the modeling, so if you assume these emission lines are primarily emitted from within the host galaxies, the mean brightness temperature due to that given line is kind of a luminosity-weighted quantity that is related to halo mass function, the luminosity of a galaxy emitting in a given line. And these factors here are just units of converting co-moving volume to the observed volume, which is in terms of frequency and the angles. So then the observed power spectrum will have three contributions. There is a clustering contribution. There is, of course, a shot contribution, because these are emitted from Poisson distributed sources. And there is the instrumental noise. And the clustering piece is the piece that has our cosmological signal via, again, the usual scale-dependent bias. So in other words, the intensity maps, of course, are bias tracers of underlying dark matter. So you would expect that the presence of primordial non-Gaussianity of a local shape will also induce a similar scale-dependent bias as it does for galaxies. And notice that this factor m is a transfer function which scales as k square on large scales. And this is the usual 1 over k square scale dependence that you hear about. Now, as of astrophysics dependence of the modeling, of course, you see that there is a strong dependence on the model of the luminosity and the relation between luminosity of the galaxy and halo mass and redshift that you assume. There is a dependence on the halo mass function that you assume, as well as there is a dependence on the fraction of time that a given galaxy is emitting in a given line, or the fraction of halos that are hosting galaxies that can emit in a given line. So, having said that, we also model the instrument noise, which is basically proportional to the noise per voxel, and the voxel is just volume in 3D, instead of the basically equivalent of a pixel, but now in 3D, times the volume of the voxel. And the noise per voxel is related to the system temperature of the instrument, integration time, the frequency precision, and the number of polarization and number of beams. And the volume of the voxel, of course, the volume of the voxel depends on the volume covered by the survey, which is basically the sky coverage, omega survey, in addition to the volume factors. And then we assume that the noise basically picks up at large and small scale. So these factors, alpha max and alpha min, are there to account for the fact that we lose certain modes on large and smallest scales due to various reasons. Now, the first part is, wow, okay, I'm very slow, so let me just skip. So the first part was specific instruments. The interesting part to take from this was that the first instrument we considered was a proposed CMB experiment, PIXI, because PIXI is able to do C2 intensity mapping because of the wide range of frequencies it covers. And the second experiment was a variation of the current pathfinder for CO intensity mapping, COMAP. Now, what are the numbers? You are probably interested in the numbers. Well, the answer is that these current designs are able to constrain FNL of order 3 or so. And if you do a multi-tracer analysis with LSST, for instance, because PIXI's signal comes from mainly redshift around 2, you can think of cross-correlating it and doing multi-tracer analysis with galaxy surveys, and it turns out that LSST is the best candidate for this cross-correlation or for the multi-tracer, and you can bring it down to below 1. And for this setup, basically the cosmic variance limit is 0.3, so you're not doing that bad. Now, this was a very simple forecast, so of course, then you have to get a bit more sophisticated to understand what are the survey and instrument design requirements, what are the modeling dependencies. So I'll just quickly tell what it is. Basically, we parameterize a given survey in terms of 5 parameters: the noise instrument, the sky fraction, the redshift coverage, and the minimum and maximum scales that are available to you. The minimum and maximum scales are determined by resolution of your instrument as well as the antenna size. And the minimum scales are basically accounting for the modes that you're going to lose due to foregrounds. Then we parameterize basically the cost of the survey as this chi instrument, which is proportional to, so this nu max over nu min characterizes the redshift coverage of the survey or frequency coverage, the integration time, and the number of beams. And basically what we are here showing is that what is basically our question, well, what is the optimal value of FNL you can achieve for a fixed cost and varying the F-sky and the redshift coverage. The point to be taken here is that there is a linear dependence on F-sky, as you would expect. There is a 1 over square root of chi dependence. So this n-beam is basically, this combination is the cost function. And it has so the constraint on FNL has a 1 over square root of chi. And then the median redshift doesn't really matter, but what you care about is the redshift coverage or frequency coverage. So just going a bit fast, and then we studied basically how sensitive you are to this particular setup, meaning if you perturb the survey and instrument characteristics, do you lose your constraining power dramatically? And the answer is no. So these plots just show how sensitive you are to variation of one parameter of the design or two parameters. Now this is one of the most important ingredients in modeling the amplitude of the signal, which is basically how do you model the specific luminosity of galaxies that are emitting a given line. There is a commonly used procedure, which is for CO line, for instance, you relate the CO luminosity to the far infrared luminosity. Then you kind of build some scaling relations between far infrared luminosity and star formation. And then you have some relations for star formation versus halo mass. Now, the first question is, what do you assume for the star formation rate and its relation to the mass and redshift? Here, we use the basically empirical data, but by Behrouzi et al., which give you the star formation rate as a function of mass and redshift by using compilation of astrophysical data. Now, the important point to take from this is just that depending on what model you assume, for instance, for the relation between CO luminosity and the halo mass, you get a significantly different amplitude for this luminosity, and this is going to translate in the amplitude of signal, and hence your ability to constrain a given cosmological parameters. So the other thing you are dependent is on the halo mass function. So depending on what halo mass function you assume, the contribution from higher and lower redshift galaxies is going to vary. So these different lines basically show the mean brightness temperature as a function of redshift for two different mass functions, and for three different assumptions for the minimum mass of the halos that's going to host a given galaxy. Now, the takeaway point from this is that, again, the specific luminosity seems to be the most important modeling ingredient that's going to affect your signal dramatically. So let me just skip this since I have very little time. Then the second biggest thing, or maybe some people would argue this is the first biggest thing, is the assumption of the foregrounds. And in particular, Schweitzer et al. In 2017 has shown that there is a scale-dependent bias that's going to be induced on large scales once you try to remove foregrounds. And he studied this in particular in the context of Pixie. So I would not go through this, but if you're interested, I can tell you more in the coffee time or in lunchtime, that we try to basically characterize this dependence on the foreground by two effective parameters and study how much your constraints change. And of course, there are other challenges. Suching here has worked for a long time on modeling interloper lines, which are basically if you are measuring if you're making a measurement in a given frequency range and you are interested in a given line, that line is not the only thing that's going to appear in that frequency range. There are going to be interloper lines from other lines. So how do you correct for that? And there are various methodologies. For us, we followed kind of a foreground avoidance. And studied how much it changes the constraints. So just to summarize, I think I'm going 1 minute over even. So it seems like from an analysis, you can achieve FNL of order unity or better, but that seems a bit too futuristic. In a sense, the survey designs that you need are far from what is currently on paper and what is currently planned for intensity mapping surveys with CO and C2. However, you can get to FNL of about 3. Spectral coverage is a very important thing to account for, but and we heard about GR effects that we have not accounted for, so in principle you should also account for them when you're looking for non-Gaussianity. And higher order clustering statistics like bispectrum or position-dependent power spectrum and so on can in principle improve these constraints. So that was all I had to say. Sorry for a couple of minutes delay.
No, thank you, Anita. Time for questions. That was a very clear talk.
Yeah, it seems so.
Okay, well, so I think we're reconvening at 2 p.m. Okay, for the afternoon session. Let's thank Azadeh and all of the speakers one last time.